Hello there. It is good to have you with us again. Find a comfortable position, let your breathing slow, and allow the weight of the day to settle somewhere far away. Tonight, we are asking a question that has puzzled astronomers for decades. What happens when you travel so far from everything that even emptiness becomes the dominant feature of reality? We are journeying to the cosmic voids, regions of space so vast and so devoid of matter that a single one could swallow hundreds of thousands of galaxies, yet contains almost nothing at all. We will begin here, in our own Milky Way, orbiting a modest yellow star in the Orion Spur. From there, we will drift outward, past the familiar neighborhood of the local group, through the great walls and filaments of galaxies, until we reach the threshold of the largest empty spaces in the known universe. Places where the distance between galaxies stretches to 300 million light-years or more. Places where the expansion of space itself seems to accelerate, pulling matter away faster than gravity can hold it together. These voids are not simply empty, they are actively emptying, growing larger as the universe ages, and they may hold secrets about dark energy, the mysterious force driving everything apart. If these quiet explorations help you find rest at the end of a long day, I would be grateful if you would consider liking this video and subscribing to the channel. It helps others find their way here too. Now let the stars come into focus. Let the hum of the earth fade beneath you. We are leaving home, and the darkness ahead is waiting. In the vast darkness between stars, gravity works its patient art. Across distances that dwarf human comprehension, matter draws together, pulled by forces that have been shaping the cosmos for nearly 14 billion years. And among all the structures that gravity has built, galaxy clusters stand as its grandest bound creations, the largest objects in the universe held together by their own mass. Consider what a galaxy cluster truly is. Not merely a collection of galaxies drifting through space, but a gravitationally bound system where hundreds or even thousands of galaxies orbit a common center of mass, trapped in a shared gravitational well from which they cannot escape. The Coma Cluster, located approximately 321 million light-years from Earth in the direction of the constellation Coma Berenices, contains over 1,000 galaxies bound together in a sphere roughly 20 million light-years across. Each of these galaxies holds billions of stars, yet the galaxies themselves are merely bright specks scattered through an enormous volume of space, like fireflies suspended in a dark cathedral. The mass required to bind such a structure is staggering. A typical rich galaxy cluster weighs between 100 trillion and 1 quadrillion solar masses, that is, between 10 to the 14th and 10 to the 15th times the mass of our Sun. To grasp this number, imagine weighing every grain of sand on every beach on Earth, then multiplying that weight by a factor of billions. The Virgo cluster, the nearest large cluster to our own local group at a distance of approximately 54 million light-years, contains a mass of roughly 1.2 quadrillion solar masses distributed across its 2,000-member galaxies and the vast spaces between them. Yet here lies one of the great mysteries that clusters revealed to astronomers. When Fritz Zwicky studied the Coma cluster in 1933, he measured the velocities of its galaxies, and found something deeply puzzling. The galaxies were moving too fast. At speeds averaging around 1,000 kilometers per second, they should have escaped the cluster's gravitational grip long ago, flying apart like water droplets flung from a spinning wheel. The visible matter, the stars and gas that telescopes could detect, accounted for only a small fraction of the mass needed to hold the cluster together. Zwicky calculated that the cluster must contain at least 400 times more mass than the luminous matter suggested. He called this unseen component, quote, zero-dark matter. Modern observations have refined this picture considerably. We now understand that in a typical galaxy cluster, the visible galaxies contribute only about 3 to 5% of the total mass. Another 12 to 15% exists as hot gas, filling the space between galaxies, the intra-cluster medium heated to temperatures of tens of millions of degrees. The remaining 80% or more is dark matter, an invisible substance that interacts with ordinary matter only through gravity, forming an enormous halo that envelops the entire cluster like an unseen cocoon. The formation of galaxy clusters unfolds across billions of years, driven by the relentless mathematics of gravitational attraction. In the early universe, tiny fluctuations in density, variations of perhaps 1 part in 100,000, provided the seeds. Where matter was slightly denser, gravity pulled in more material from the surrounding regions. Where it was slightly less dense, matter flowed outward. Over cosmic time, these small differences amplified. Dense regions grew denser still, collapsing under their own weight, while underdense regions emptied further, becoming the voids that now separate clusters. The process resembles water droplets condensing on a cold window. At first, the moisture is distributed almost uniformly across the glass, but small imperfections, microscopic scratches, dust particles, variations in temperature, cause droplets to form at certain points. These droplets grow by absorbing moisture from their surroundings, becoming larger while the spaces between them dry out. In the cosmic case, the quote 1 is matter, the quote 2 are primordial density fluctuations, and the quote 3 are galaxy clusters, growing over billions of years as gravity draws material inward from the expanding universe. The Abel Catalogue, compiled by astronomer George Abel in 1958 and later expanded, lists over 4,000 rich galaxy clusters visible from Earth. Each entry represents a gravitationally bound system containing at least 30 galaxies within a radius of about 1.5 megaparsecs, roughly 4.9 million light-years. The richest clusters, classified as Abel Richness Class 4 or 5, contain 200 or more bright galaxies in this volume. Abel 2029, located about 1 billion light-years away, hosts a giant elliptical galaxy at its center that spans over 1 million light-years across, 10 times the diameter of the Milky Way, and contains several trillion stars. At the heart of many clusters sits a dominant galaxy, grown enormous through billions of years of cosmic cannibalism. These brightest cluster galaxies, or BCGs, have consumed dozens or hundreds of smaller galaxies that fell too close to the cluster center. The process is called galactic cannibalism, and it proceeds through dynamical friction, a gravitational drag that slows orbiting galaxies and causes them to spiral inward over hundreds of millions of years. The giant elliptical galaxy M87 at the center of the Virgo cluster has grown to 6 trillion solar masses through this process. And at its core lurks a supermassive black hole weighing 6.5 billion solar masses, the first black hole ever directly imaged by the Event Horizon Telescope. The distribution of galaxy clusters across the sky is not random. They trace the densest nodes of a vast cosmic network connected by filaments of galaxies and dark matter that stretch across hundreds of millions of light years. Where filaments intersect, clusters form. Where multiple filaments converge, the largest clusters arise. Massive systems like the Shapley supercluster, a concentration of over 8,000 galaxies located 650 million light-years away, representing one of the densest regions of the nearby universe. Gravity never rests. Even now, clusters continue to grow, pulling in galaxies from their surroundings, merging with other clusters in collisions that release energies beyond human comprehension. The Bullet Cluster, located 3.7 billion light-years from Earth, shows 2 clusters that passed through each other approximately 150 million years ago. In this cosmic collision, the hot gas from each cluster, visible in X-ray observations, was slowed by electromagnetic interactions, while the dark matter passed through unimpeded, separating from the ordinary matter. This separation provided some of the strongest evidence that dark matter is real and distinct from ordinary matter, not merely an artifact of our incomplete understanding of gravity. Temperature measurements reveal the violence hidden within these seemingly serene structures. The gas between cluster galaxies burns at 10 to 100 million Kelvin, so hot that it emits X-rays rather than visible light. This intracluster medium was heated by gravitational compression as the cluster formed, and by shock waves from merging subclusters. A single rich cluster radiates X-rays with a luminosity of 10 to the 43rd to 10 to the 45th ergs per second, roughly equivalent to 1 trillion suns shining in X-ray light alone. And so the clusters drift through the expanding universe, the largest gravitationally bound structures that will ever exist. In the distant future, as dark energy accelerates cosmic expansion, clusters will become isolated islands, their member galaxies merging into single giant ellipticals, while the space between clusters stretches beyond any possibility of contact. But for now, they remain connected, nodes in a cosmic web that spans the observable universe, monuments to gravity's patient work across the ages. Between the galaxies that populate these great clusters lies a substance invisible to human eyes, yet containing more mass than all the stars combined. This is the intracluster medium, a diffuse ocean of ionized gas so hot that it glows not in visible light, but in X-rays, filling the gravitational wells of clusters with plasma heated to temperatures between 10 million and 100 million Kelvin. To understand this hidden reservoir, consider the Coma cluster, located approximately 321 million light-years from Earth, in the direction of the constellation Coma Berenices. When astronomers first studied Coma in the 1930s, they counted its galaxies and estimated their masses from their brightness. But the galaxies were moving too fast. Velocities of 1,000 to 3,000 kilometers per second, far too rapid to be held together by the visible matter alone. The cluster should have flown apart billions of years ago. Something unseen was providing the gravitational glue. Part of that missing mass, we now know, resides in the intracluster medium itself. In a typical rich cluster, the hot gas accounts for roughly 12 to 15% of the total mass, while the galaxies contribute only 3 to 5%. The remaining 80% or more is dark matter, but the gas alone outweighs all the stars in all the galaxies by a factor of 5 or 6. If you could somehow gather all the luminous matter in a cluster like Coma, every star, every planet, every grain of dust, the hot gas filling the space between would still be several times more massive. This gas did not always exist in its current state. Much of it fell into the cluster's gravitational potential well during the early stages of formation, drawn inward along with the dark matter and galaxies as the structure coalesced from primordial density fluctuations. As the gas fell, it accelerated, and as it encountered other infalling material, it shocked and heated. The process is analogous to air heating when compressed in a bicycle pump, but on scales spanning millions of light years and reaching temperatures that would vaporize any known material. The temperature of the intracluster medium correlates directly with the mass of the cluster that contains it. More massive clusters have deeper gravitational wells, and gas falling into these wells converts more gravitational potential energy into thermal energy. The relationship follows a precise scaling. The temperature in Kelvin is roughly proportional to the cluster mass raised to the 2/3 power. A cluster with a mass of 10 to the 14th solar masses, 100 trillion times the mass of our Sun, typically hosts gas at temperatures around 20 million Kelvin. A cluster 5 times more massive might reach 50 million Kelvin or higher. At these temperatures, the gas is fully ionized. Hydrogen atoms, which make up about 75% of the medium by mass, have been stripped of their electrons. Helium, comprising most of the remaining 25%, exists as bare nuclei. Heavier elements, oxygen, iron, silicon, sulfur, are present in trace amounts, typically at about 1/3 the abundance found in the Sun, and they too are highly ionized, with iron atoms missing 24 or 25 of their 26 electrons. These heavy elements did not exist when the universe began. They were forged in the cores of stars and expelled into space through stellar winds and supernova explosions. Their presence in the intracluster medium tells a story of cosmic enrichment spanning billions of years. Galaxies processed primordial hydrogen and helium into heavier elements, then ejected those elements through violent outflows driven by supernovae and active galactic nuclei. The enriched gas mixed with the pristine intracluster medium, raising its metallicity to the levels observed today. The distribution of these metals provides clues to the history of the cluster. Iron, produced primarily in type Ia supernovae, the thermonuclear explosions of white dwarf stars, tends to be more centrally concentrated, reflecting the longer timescales of its production and the gravitational settling of enriched gas toward the cluster core. Oxygen and silicon, produced more rapidly in core collapse supernovae from massive stars, show flatter distributions, suggesting earlier enrichment when the cluster was still assembling. The density of the intracluster medium varies enormously from the cluster center to its outskirts. In the core of a relaxed cluster like Abel 1795, located about 840 million light-years away, The electron density reaches approximately 0.05 particles per cubic centimeter, still a vacuum by terrestrial standards, but dense enough to produce significant X-ray emission. At the cluster's edge, perhaps 6 million light-years from the center, the density drops to 0.0001 particles per cubic centimeter, 1,000 times more rarefied. Despite this extreme thinness, the sheer volume of the intracluster medium makes it a powerful radiator. X-ray emission occurs primarily through a process called thermal Bremsstrahlung, or braking radiation. When free electrons pass close to ions, they are deflected by electromagnetic forces and emit photons. The rate of this emission depends on the square of the density and the square root of the temperature, meaning that the densest, hottest regions shine most brightly. The Chandra X-ray Observatory, launched in 1999, has revealed the intracluster medium in exquisite detail. Its images show not a smooth, featureless glow, but a complex landscape of structures. Cold fronts mark boundaries where cooler gas meets hotter material, often produced when a smaller cluster or galaxy group falls into a larger system, and its gas is stripped by ram pressure. Shock fronts trace the passage of merger events, where two clusters have collided, and their gases are still equilibrating millions of years later. In the Perseus cluster, located 240 million light-years away, and one of the brightest X-ray sources in the sky, Chandra observations revealed something unexpected. Ripples in the gas, concentric pressure waves spreading outward from the central galaxy NGC 1275. These ripples are sound waves generated by the rhythmic inflation of bubbles by the supermassive black hole at the galaxy's center. The black hole, with a mass of approximately 800 million suns, periodically launches jets of relativistic particles that push aside the surrounding gas, creating cavities filled with radio-emitting plasma. The sound waves in Perseus have a frequency of about 1 oscillation every 10 million years, far below any frequency audible to human ears, but sound nonetheless, pressure variations propagating through a medium. The note they produce, if transposed 57 octaves upward into the range of human hearing, would be a B-flat, roughly 57 octaves below middle C. This is the deepest note ever detected in the universe, a cosmic drone that has been playing for hundreds of millions of years. These sound waves serve a crucial function. As they propagate outward, they dissipate their energy into the gas, providing gentle heating that prevents the intracluster medium from cooling catastrophically. Without this heating, the gas in cluster cores would radiate away its thermal energy in a few 100 million years, cool to temperatures where it could form stars and collapse into the central galaxy. This cooling flow problem puzzled astronomers for decades until Chandra revealed the feedback mechanism. Black holes regulate the temperature of their surroundings, injecting just enough energy to maintain equilibrium. The balance is delicate. Too little heating, and the gas cools and collapses. Too much, and the gas is expelled from the cluster entirely. Yet across cosmic time, the system self-regulates. When cooling increases, more gas falls toward the center, feeding the black hole and increasing its output. When heating dominates, the fuel supply diminishes, and the black hole quiets. This feedback loop has maintained the intracluster medium in a quasi-steady state for billions of years. At the edges of clusters, Where the intracluster medium meets the even more diffuse gas of the cosmic web, the physics changes. Here, the gas is still falling inward, accreting onto the cluster along filaments of the large-scale structure. Accretion shocks mark the boundaries where this infalling material first encounters the cluster environment, heating from temperatures of perhaps 100,000 Kelvin to tens of millions of Kelvin in a transition zone only a few 100,000 light-years thick. These outer regions remain poorly understood, their faint emission challenging to detect against the X-ray background. But they contain clues to cluster formation and growth, to the rate at which matter continues to accumulate even in the present epoch. The intracluster medium is not static. It is a living system, still evolving, still being shaped by gravity and feedback, and the slow rain of matter from the cosmic web. And so the hot gas drifts between the galaxies, glowing softly in wavelengths no eye can see, carrying within it the processed elements of countless stellar generations, heated by the deepest gravitational wells in the universe, stirred by the most massive black holes, singing in frequencies too low for any ear. It is the hidden ocean of the clusters, vaster than all the stars it surrounds. Yet beneath this luminous gas, beneath the visible galaxies and the stars that populate them, lies something far more massive and far more mysterious. The intracluster medium glows because it has fallen into a gravitational well it did not create. The galaxies orbit within a potential they cannot account for with their own mass. Something else holds these structures together, something that neither emits nor absorbs light, something that interacts with ordinary matter only through the gentle, persistent pull of gravity. Dark matter constitutes approximately 84% of all matter in the universe. In a typical galaxy cluster, for every kilogram of hot gas and every kilogram of stars, there exist roughly 5 kilograms of this invisible substance. The Coma cluster, that great congregation of over 1,000 galaxies, some 320 million light-years distant, contains perhaps 700 trillion solar masses of dark matter, compared to roughly 140 trillion solar masses of ordinary baryonic material. The galaxies themselves, luminous and seemingly dominant, account for only a few percent of the total mass. They are bright tracers embedded within vast, invisible structures. These structures are called dark matter halos. They are not solid objects, but diffuse clouds of particles that have never been directly detected. Particles that pass through ordinary matter like wind through an open window. Yet their gravitational influence is unmistakable. The velocities of galaxies within clusters, the temperature of the intracluster medium, the bending of light from distant sources, all reveal the presence of mass far exceeding what can be seen. A dark matter halo surrounding a galaxy cluster extends far beyond the visible boundaries of that cluster. Where the X-ray emission fades and the galaxy density drops to near zero, the dark matter continues outward, its density declining gradually with distance from the center. The virial radius of a massive cluster, the boundary within which the system has reached gravitational equilibrium, typically spans 2 to 3 megaparsecs, or roughly 6 to 10 million light-years. Within this volume, dark matter particles orbit in complex, overlapping trajectories, their collective gravity binding the entire system together. The density profile of these halos follows a characteristic pattern, first described by Julio Navarro, Carlos Frenk, and Simon White in 1996. Near the center, the density rises steeply, though not quite to a sharp point. Moving outward, the density falls more gradually, declining roughly as the inverse cube of the distance from the center. This NFW profile, as it is known, emerges naturally in computer simulations of cosmic structure formation, arising from the physics of gravitational collapse in an expanding universe. The formation of these halos began in the earliest epochs of cosmic history, when the universe was less than 400,000 years old, still filled with the hot plasma that would eventually cool to form the cosmic microwave background. Tiny fluctuations in density already existed. These fluctuations were the seeds planted by quantum processes during cosmic inflation, stretched to macroscopic scales and frozen into the fabric of space. Where the density was slightly higher than average, perhaps 1 part in 100,000, gravity began its slow work of amplification. Dark matter, unlike ordinary matter, does not interact with light. It cannot be heated by radiation or cooled by emission. While the baryonic component of the early universe remained locked in thermal equilibrium with the photon bath, dark matter was free to begin collapsing. The slightly overdense regions grew denser still, pulling in material from their surroundings. By the time the universe was a few 100 million years old, the first dark matter halos had formed. Small structures containing perhaps 1 million solar masses, the gravitational cradles within which the first stars would eventually ignite. These early halos did not remain isolated. Gravity continued its work, drawing smaller halos together into larger ones. This process of hierarchical merging is the fundamental mechanism of structure formation in the universe. Small structures form first, then combine into progressively larger ones. A galaxy like the Milky Way, residing within a dark matter halo of roughly 1 trillion solar masses, assembled from the merger of hundreds of smaller halos over billions of years. The stellar halo of our galaxy, that diffuse cloud of ancient stars surrounding the disk, contains the debris of these long-ago mergers, streams and shells of stars torn from smaller galaxies as they fell inward and were disrupted. Galaxy clusters represent the current endpoint of this hierarchical assembly. They form at the intersections of cosmic filaments, where multiple streams of matter converge. The dark matter halos of clusters have grown through the continuous accretion of smaller halos, each merger adding mass and energy to the system. The Virgo cluster, the nearest large cluster to our own local group at a distance of roughly 54 million light-years, contains a dark matter halo of approximately 1 quadrillion solar masses, 1,000 trillion times the mass of our Sun. It has assembled this mass over more than 10 billion years, swallowing countless smaller groups and individual galaxies. The process of cluster formation is violent, though it unfolds on timescales that render it imperceptible to human observation. When 2 cluster-massed halos merge, the collision releases gravitational potential energy equivalent to roughly 10 to the power of 64 joules. More energy than a supernova releases in its entire explosion, sustained over hundreds of millions of years. This energy heats the intracluster medium, drives shockwaves through the gas, and temporarily disrupts the equilibrium of the system. The Bullet Cluster, located some 3.7 billion light-years away, preserves evidence of such a collision. Two clusters passed through each other roughly 150 million years ago, and the aftermath remains visible. The hot gas of each cluster, slowed by its own pressure, lags behind the dark matter and galaxies which passed through each other like two swarms of bees, their individual members too widely separated to collide. This separation of dark matter from baryonic matter in the Bullet Cluster provided some of the most compelling evidence for dark matter's existence. Gravitational lensing, the bending of light from background galaxies, reveals where the mass is concentrated. In the Bullet Cluster, the mass is centered not on the hot gas, which contains most of the baryonic material, but on the positions of the galaxies, which trace the dark matter distribution. If gravity were simply modified rather than supplemented by invisible matter, the lensing signal would follow the gas. It does not. Within the dark matter halos of clusters, smaller halos persist as substructure. Each galaxy retains its own dark matter envelope, a halo within a halo. These subhalos orbit within the larger cluster potential, gradually losing mass through tidal stripping as the gravitational forces of the cluster pull material from their outer regions. A galaxy falling into a cluster for the first time may retain most of its dark matter halo initially, but over several billion years, repeated passages through the cluster center will strip away the outer layers, leaving only a compact core. The process is slow, but inexorable. The concentration of dark matter halos, the ratio of their central density to their average density, provides information about their formation history. Halos that formed earlier, when the universe was denser, tend to be more concentrated than those that formed later. Cluster mass halos, being the most recent large structures to form, are typically less concentrated than the halos of individual galaxies. The Coma cluster has a concentration parameter of roughly 4 to 5, meaning its central density is only a few times higher than its average density within the virial radius. A galaxy like the Milky Way, by contrast, has a concentration closer to 10 or 12. The temperature of the intracluster medium reflects the depth of the dark matter potential well. Gas falling into a cluster converts gravitational potential energy into thermal energy, heating to temperatures that depend on the total mass of the system. The relationship is precise. A cluster with a temperature of 100 million Kelvin contains roughly 10 times the mass of a cluster at 10 million Kelvin. By measuring X-ray temperatures, astronomers can weigh clusters, determining the total mass, most of it dark, that holds these systems together. And so the dark matter halos drift through the cosmos, invisible yet dominant, their gravity shaping the distribution of everything we can see. The galaxies follow the dark matter. The hot gas follows the dark matter. The light bends around the dark matter. It is the skeleton upon which the visible universe is built, the scaffolding that emerged from quantum fluctuations in the first fraction of a second and grew through billions of years of gravitational collapse and hierarchical merging into the largest bound structures that exist. But these bound structures, massive as they are, do not exist in isolation. They are themselves drawn toward something larger, something that operates on scales where even clusters become small. Across distances of hundreds of millions of light-years, clusters gather into chains, into sheets, into vast assemblages that astronomers call superclusters. These are not bound systems in the way that clusters are bound. The gravity that holds a cluster together, that keeps its galaxies orbiting and its hot gas contained, is strong enough to resist the expansion of space itself. But superclusters exist at the threshold where gravity and cosmic expansion wage a more even battle, where structures stretch and flow rather than collapse and bind. The distinction matters enormously for understanding what superclusters truly are. A galaxy cluster like Coma, with its 1,000 galaxies and its 100 million degree gas, will remain gravitationally bound for the rest of cosmic time. Its galaxies will orbit, merge, and eventually coalesce. But a supercluster is different. It is a transient arrangement, a snapshot of matter caught in the act of flowing toward greater concentrations of mass. The galaxies and clusters within a supercluster are moving toward common gravitational attractors, but many of them will never arrive. The accelerating expansion of space, driven by dark energy, is gradually pulling superclusters apart even as gravity tries to draw them together. Consider the numbers that define these structures. A typical supercluster spans between 100 and 200 megaparsecs, roughly 300 to 600 million light-years. Within this volume, one might find anywhere from 2 to 15 major galaxy clusters, connected by filaments of galaxies and threaded with the same cosmic web that structures the universe at all scales. The total mass of a supercluster ranges from 10 to the 15th to 10 to the 16th solar masses, 10 quadrillion to 100 quadrillion times the mass of our Sun. This sounds enormous, and it is, yet it represents a density only slightly higher than the cosmic average. Superclusters are overdense regions, but only modestly so, typically containing perhaps twice the average density of matter in the universe. The Virgo supercluster, our own local neighborhood, provides a familiar example. It stretches roughly 110 million light-years across and contains at least 100 galaxy groups and clusters. At its heart lies the Virgo cluster itself, a collection of over 1,000 galaxies, centered about 54 million light-years from Earth. The Milky Way belongs to a small group called the Local Group, which in turn is falling toward the Virgo cluster at a velocity of roughly 300 kilometers per second. This motion is not random wandering, but a direct response to the gravitational pull of the mass concentrated in Virgo's direction. Yet even the Virgo supercluster is merely a component of something larger. In 2014, astronomers using data from the Cosmic Flows 2 survey mapped the peculiar velocities of 8,000 galaxies, their motions relative to the smooth expansion of space, and discovered that the Virgo supercluster is itself part of a much grander structure. They named it Laniakea, from the Hawaiian words for, quote, zero, and its boundaries encompass a region 520 million light-years across, containing roughly 100,000 galaxies with a total mass of 10 to the 17th solar masses. The key to understanding Laniakea lies not in its boundaries, but in its flows. Every galaxy within this vast region is moving, pulled by gravity toward concentrations of mass, and pushed by the expansion of space away from regions of lower density. When astronomers map these motions, they find that they converge. Like streams flowing into rivers, like rivers flowing toward the sea, the peculiar velocities of galaxies within Laniakea all point toward a common destination. This convergence defines the supercluster's extent. Its boundary is the surface where the flow changes direction, where galaxies begin falling toward some other attractor rather than toward Laniakea's center. The physics governing these flows is elegant in its simplicity. In an expanding universe, a region with slightly higher than average density will expand slightly more slowly than its surroundings. Matter from adjacent regions will gradually flow toward this overdensity, increasing its mass and strengthening its gravitational pull. Over billions of years, these flows carve the universe into basins of attraction, each supercluster representing a watershed in the cosmic landscape. The analogy to water flowing downhill is remarkably apt. Galaxies roll down the gravitational potential toward the deepest wells, their velocities a direct measure of the slope they are descending. These peculiar velocities, the motions of galaxies relative to the Hubble flow, typically range from 100 to 600 kilometers per second. The Milky Way itself moves at about 630 kilometers per second, relative to the cosmic microwave background, a motion that combines our fall toward Virgo, Virgo's fall towards the center of Laniakea, and Laniakea's own motion toward even larger structures. Disentangling these components requires careful measurement of thousands of galaxy distances and redshifts, building up a three-dimensional map of cosmic flows. The Shapley supercluster, located roughly 650 million light-years away in the direction of the constellation Centaurus, represents one of the most massive concentrations of matter in the nearby universe. It contains more than 25 distinct galaxy clusters, with a total mass exceeding 10 to the 16th solar masses. The gravitational influence of Shapley contributes significantly to the motion of our own local group, pulling us at roughly 200 kilometers per second toward its location. Some astronomers have proposed that Shapley and Laniakea may themselves be part of an even larger structure, though at these scales the distinction between genuine physical association and chance alignment becomes increasingly difficult to establish. The internal structure of superclusters reveals the same hierarchical patterns found at smaller scales. Clusters do not distribute randomly within a supercluster, but arrange themselves along filaments and sheets, with voids between them. The Perseus-Pisces supercluster, stretching across 300 million light-years, consists of a long chain of clusters arranged almost like beads on a string, a filamentary structure that traces the underlying dark matter distribution. The Horologium Reticulum supercluster, one of the largest known, spans over 500 million light-years and contains at least 30 massive clusters connected by a complex network of galaxy filaments. Time operates differently at these scales. While a galaxy cluster might form over 2 to 3 billion years, superclusters are still assembling today, their constituent parts still flowing toward common centers. The Coma supercluster, dominated by the rich Coma cluster at its core, continues to draw in surrounding groups and smaller clusters. In another few billion years, some of these infalling systems will merge with Coma itself, adding to its mass. But others, those at the supercluster's periphery, will never complete their journey. The accelerating expansion of space will eventually overcome the gravitational attraction, and these outer regions will drift away, their connection to the supercluster severed forever. This competition between gravity and expansion creates a natural maximum size for gravitationally influenced structures. At scales below about 300 megaparsecs, gravity dominates, and matter flows toward overdense regions. Above this scale, the universe becomes increasingly homogeneous, and the expansion of space overwhelms local gravitational effects. Superclusters exist precisely at this transition, large enough to represent significant departures from cosmic uniformity, yet too large to ever collapse into bound systems. The temperature of the gas within superclusters reflects this intermediate state. While cluster cores contain gas heated to tens of millions of degrees, the filaments connecting clusters hold gas at merely millions of degrees, warm by cosmic standards but cool compared to cluster centers. This warm, hot intergalactic medium, as astronomers call it, contains perhaps half of all the ordinary matter in the universe, yet it remains extraordinarily difficult to detect. Its temperature is too low to emit significant X-rays, and its density is too low to absorb much light from background sources. It exists in a kind of observational shadow, its presence inferred more than directly measured. And so the superclusters drift through the expanding cosmos, their clusters and galaxies flowing along gravitational gradients carved by dark matter, their boundaries defined not by edges, but by watersheds in the cosmic velocity field. They are the largest structures that gravity has managed to influence, the final tier in the hierarchy of cosmic organization before the universe dissolves into statistical uniformity. Within them, the same processes that built galaxies and clusters continue to operate, matter falling into potential wells, gas heating as it compresses, dark matter halos merging and growing. But the clock is running out. The expansion of space accelerates year by year, and the gravitational reach of even the largest superclusters grows ever shorter. Among these vast gravitational watersheds, one particular basin claims our attention, not because it is the largest or the most massive, but because it is ours. The Milky Way, with its 400 billion stars and its supermassive black hole and its spiral arms sweeping through a disk 100,000 light-years across, belongs to a structure so immense that light itself requires 520 million years to traverse it. This structure bears the name Laniakea, a Hawaiian word meaning immense heaven, and it represents the gravitational address of everything we have ever known. To understand Laniakea is to understand how astronomers learned to see motion itself as a kind of map. For decades, researchers had catalogued the positions of galaxies, building three-dimensional atlases of the local universe. But position alone tells only part of the story. Every galaxy moves, pulled by the gravitational influence of matter both visible and dark. And these motions, these peculiar velocities that deviate from the smooth expansion of space, trace the underlying distribution of mass like iron filings, revealing magnetic field lines. The breakthrough came from measuring what astronomers call the velocity field. By carefully determining how fast galaxies move relative to the expanding background of space, researchers could work backward to infer where mass must be concentrated. Regions of high density pull galaxies toward them. Regions of low density let galaxies drift away. The pattern of these flows, mapped across millions of light years, reveals the gravitational topography of the cosmos. What emerged from this analysis was a picture of basins and ridges, of gravitational valleys and watersheds. Laniakea appears as one such basin, a region of space within which all galaxies flow toward a common gravitational attractor. The boundary of Laniakea is not a wall or an edge, but a divide, a surface where the gravitational pull from our supercluster exactly balances the pull from neighboring structures. Galaxies on one side of this divide fall toward Laniakea's center. Galaxies on the other side fall away, drawn toward different attractors, belonging to different superclusters entirely. The numbers that define Laniakea stagger the imagination even as they ground it in physical reality. The supercluster contains approximately 100,000 galaxies, their combined mass reaching perhaps 100 million billion solar masses, a 1 followed by 17 zeros, each solar mass itself representing 2,000 trillion kilograms. This matter spreads across a volume roughly 520 million light-years in diameter, though the boundaries remain fuzzy, defined by velocity gradients rather than sharp edges. Within this vast basin, structure organizes itself hierarchically. The Milky Way belongs to the local group, a modest collection of perhaps 80 galaxies dominated by our own spiral and the Andromeda Galaxy, which lies 2.5 million light-years distant and approaches us at 110 kilometers per second. The local group itself belongs to the Virgo supercluster, a flattened structure centered on the Virgo cluster some 54 million light-years away. And the Virgo supercluster, once thought to be our cosmic home, turns out to be merely an appendage of Laniakea, an outlying region within a far larger gravitational system. The center of Laniakea, or rather the point toward which all its galaxies flow, lies in the direction of the constellations Norma and Centaurus, roughly 250 million light-years from Earth. This region, long known as the Great Attractor, represents the gravitational focus of our supercluster, the bottom of the potential well into which matter has been sliding for billions of years. The Milky Way moves toward this center at approximately 630 kilometers per second, a velocity that sounds enormous until one calculates that at this rate, reaching the Great Attractor would require more than 100 billion years, far longer than the current age of the universe, far longer than the time remaining before cosmic expansion carries these structures beyond each other's gravitational reach. This motion toward the Great Attractor combines with other flows to produce the complex velocity pattern observed in our cosmic neighborhood. The local group also moves toward the Shapley supercluster, a massive concentration of galaxy clusters lying beyond the Great Attractor at a distance of some 650 million light-years. The gravitational influence of Shapley adds to the pull of the Great Attractor, creating a bulk flow that carries our entire region of space through the cosmos at speeds that can only be measured against the cosmic microwave background. That ancient light that provides the only truly stationary reference frame. The shape of Laniakea reflects the processes that built it. Rather than a sphere, the supercluster extends in filamentary structures, with chains of galaxy clusters connected by bridges of dark matter and diffuse gas. The Milky Way sits in a relatively sparse region, far from the dense core, in an area where the local density exceeds the cosmic average by only modest factors. We inhabit the suburbs of our supercluster, the quiet outskirts where galaxy encounters remain rare, and the night sky holds only the familiar patterns of our own stellar neighborhood. Mapping Laniakea required observations of more than 8,000 galaxies, each with carefully measured distances and velocities. The distances came from the Tully-Fisher relation, a correlation between how fast a spiral galaxy rotates and how intrinsically bright it appears. By measuring rotation speeds through the Doppler shift of spectral lines and comparing intrinsic brightness to apparent brightness, astronomers could determine how far away each galaxy lies. The velocities came from redshift measurements, corrected for the expansion of space to reveal the peculiar motions driven by local gravitational fields. From these measurements emerged the flow lines that define Laniakea's extent. Like streams flowing into a river basin, galaxies throughout the supercluster move along paths that converge toward the central attractor. The boundary appears where these flow lines diverge, where galaxies begin moving toward different centers, belonging to different gravitational systems. The Perseus-Pisces supercluster lies beyond one such boundary. The Shapley supercluster lies beyond another. Each represents a separate basin in the gravitational topography of the universe, each containing its own hierarchy of clusters and groups and galaxies. The mass that drives these flows remains largely invisible. Dark matter dominates Laniakea just as it dominates individual clusters and galaxies, outweighing ordinary matter by factors of 5 or 6 to 1. The visible galaxies trace the underlying dark matter distribution like foam on ocean waves, marking the peaks of density, while revealing little about the vast structures beneath. Computer simulations that model the growth of cosmic structure reproduce the observed velocity fields only when dark matter is included, its gravitational influence shaping the flows that define superclusters across the observable universe. Yet Laniakea, despite its immensity, is not gravitationally bound. The expansion of space works against the gravitational attraction that draws its galaxies together, and at the scales involved, expansion wins. The supercluster will never collapse into a single structure. Instead, it will gradually disperse, its component clusters drifting apart as cosmic expansion accelerates, its current coherence a temporary phase in the evolution of the universe. In tens of billions of years, the gravitational basin we call home will have flattened and spread, its boundaries dissolved, its galaxies scattered into an ever emptier void. For now, Laniakea remains our cosmic context, the largest structure to which we can claim any meaningful belonging. Beyond its boundaries lie other superclusters, other basins, other flows, a universe of gravitational watersheds extending to the limits of observation and presumably far beyond. The Milky Way drifts through this landscape at hundreds of kilometers per second, carried by forces that began operating when the universe was young, following paths carved by dark matter that condensed from quantum fluctuations nearly 14 billion years ago. And yet, as the Milky Way moves through Laniakea's gravitational basin, it does not drift aimlessly. Our galaxy, along with the entire local group and thousands of other galaxies stretching across hundreds of millions of light-years, streams toward a specific region of space, a concentration of mass so significant that it bends the trajectories of everything around it, yet so obscured that for decades astronomers could only infer its presence from the motions it caused. This is the Great Attractor, a gravitational anomaly located approximately 250 million light-years from Earth, in the direction of the constellations Centaurus and Norma. Its influence extends across a volume of space containing tens of thousands of galaxies, all of which exhibit peculiar velocities, motions that deviate from the smooth expansion of the universe, pointing toward this same mysterious region. The Milky Way itself moves toward the Great Attractor at roughly 600 kilometers per second, a velocity that would carry us from Earth to the Moon in just over 10 minutes, sustained continuously across cosmic time. The difficulty in studying the Great Attractor lies not in its distance, but in its location. It sits almost directly behind the plane of the Milky Way, in a region astronomers call the zone of avoidance. Here, the dust and stars of our own galaxy's disk block visible light from more distant objects, creating a band across the sky where optical telescopes see only the foreground clutter of our local stellar neighborhood. For observers trying to peer through this cosmic curtain, it is like attempting to study a distant city while standing in the middle of a dense forest. The trees closest to us obscure everything beyond. Early evidence for the Great Attractor came not from seeing it directly, but from measuring the velocities of galaxies on either side of the obscured zone. In the 1970s and 80s, astronomers conducting systematic surveys of galaxy redshifts noticed something peculiar. Galaxies in the direction of Centaurus showed redshifts smaller than expected for their distances, while galaxies in the opposite direction showed redshifts larger than expected. The pattern suggested that our entire region of space was moving coherently toward something massive hidden behind the Milky Way's disk. The mathematics of this motion revealed the scale of mass required to produce such an effect. To accelerate tens of thousands of galaxies, each containing hundreds of billions of stars, to velocities of hundreds of kilometers per second, requires a gravitational source of extraordinary magnitude. Early estimates suggested a mass equivalent to tens of thousands of Milky Way galaxies, or roughly 10 to the 16th solar masses, concentrated in a region perhaps 150 million light-years across. Infrared observations eventually pierced the zone of avoidance, revealing what optical telescopes could not see. At wavelengths of 2 micrometers and beyond, the dust that blocks visible light becomes increasingly transparent, allowing astronomers to detect the warm glow of distant galaxies. These surveys revealed that the Great Attractor region is not empty, but densely populated with galaxy clusters, the most prominent being the Norma cluster, also designated Abel 3627. The Norma cluster lies at the heart of the Great Attractor region, approximately 220 million light-years from Earth. It contains hundreds of galaxies bound together by gravity, with a total mass of perhaps 10 to the 15th solar masses, 1,000 trillion times the mass of our Sun. Its central galaxy, ESO 137-001, shows dramatic tails of gas streaming behind it as it plunges through the hot intracluster medium at nearly 2,000 kilometers per second, stripped of its star-forming material by the pressure of its passage. Yet the Norma cluster alone cannot account for all the gravitational influence attributed to the Great Attractor. The observed velocities of galaxies in the region require more mass than any single cluster can provide. The solution to this puzzle lies in recognizing that the Great Attractor is not a single object, but a concentration of multiple clusters and superclusters, all contributing to the gravitational pull that shapes the flow of matter across this region of space. Behind the Norma cluster, even deeper in the zone of avoidance, lies additional structure that infrared and radio surveys have only recently begun to map. The Centaurus Wall, a filament of galaxies extending across hundreds of millions of light years, threads through this region. The Shapley supercluster, located approximately 650 million light-years from Earth, exerts its own gravitational influence, contributing to the complex pattern of motions observed in our cosmic neighborhood. The Shapley supercluster deserves particular attention, for it may be the true dominant mass concentration pulling on Laniakea. Discovered by Harlow Shapley in the 1930s, this structure is one of the most massive concentrations of galaxies in the observable universe. It contains more than 24 rich galaxy clusters packed into a volume roughly 100 million light-years across, with a total mass estimated at 10 to the 16th solar masses, 10,000 trillion suns. Some calculations suggest that Shapley contributes as much or more to our peculiar velocity as the nearer structures of the Great Attractor region. The relationship between these various mass concentrations illustrates how gravitational influence operates across cosmic scales. The Milky Way does not simply fall toward the nearest massive object. Instead, it responds to the combined gravitational pull of everything within its cosmic horizon, weighted by mass and distance according to Newton's inverse square law. The Great Attractor, the Shapley supercluster, and countless other structures all contribute vectors to our motion, their influences adding and subtracting to produce the net velocity we observe. Measurements of the cosmic microwave background provide another window into these large-scale motions. The CMB exhibits a dipole anisotropy, a pattern where the sky appears slightly warmer in one direction and slightly cooler in the opposite direction, caused by our motion through the universe. This dipole indicates that the solar system moves at approximately 370 kilometers per second relative to the CMB rest frame, in a direction roughly toward the constellation Leo. When combined with the Sun's motion around the Milky Way and the Milky Way's motion within the local group, this measurement helps constrain the total velocity of our cosmic neighborhood relative to the expanding universe. The physics underlying these motions connects directly to the initial conditions of the cosmos. The density fluctuations that seeded the Great Attractor and other mass concentrations originated in the first fraction of a second after the Big Bang, amplified by inflation, and then grown by gravitational instability over billions of years. The same quantum processes that created slight overdensities in the primordial plasma eventually produced the vast gravitational wells that now shape the trajectories of billions of galaxies. Dark matter, as always, provides the invisible framework for these structures. The visible galaxies and hot gas of the Great Attractor region trace only a fraction of the total mass present. The majority consists of dark matter halos, extended distributions of non-luminous matter that outweigh the baryonic component by roughly 5 to 1. These halos merged and grew over cosmic time, their gravitational wells deepening as more material fell inward, creating the conditions for galaxies to form within their centers. Recent surveys using radio telescopes have pushed even deeper into the zone of avoidance, detecting hydrogen gas in galaxies that remain invisible at other wavelengths. The Parkes radio telescope in Australia and the Effelsberg telescope in Germany have mapped thousands of previously unknown galaxies behind the Milky Way's disk, revealing a rich tapestry of structure that connects the Great Attractor to the broader cosmic web. These observations confirm that the zone of avoidance, despite its name, is not truly empty, but merely hidden from our usual methods of observation. The flow of galaxies toward the Great Attractor represents just one current in the larger river of cosmic motion. On scales of hundreds of millions of light-years, the universe exhibits bulk flows, coherent motions of matter that extend across vast volumes of space. Some studies have suggested that even the Great Attractor and Shapley supercluster are themselves moving toward still larger mass concentrations at greater distances, though these claims remain debated. The challenge lies in separating true bulk flows from the random motions of individual structures, a statistical problem that requires surveying millions of galaxies with precise distance measurements. As our observational capabilities improve, the Great Attractor has transformed from a mysterious anomaly into a well-characterized feature of our cosmic environment. It is not a single object, but a region, not a destination, but a direction, not an endpoint, but a waypoint in the endless gravitational dance of cosmic structure. The Milky Way will never reach the Great Attractor in any meaningful sense. The expansion of the universe ensures that these distant structures recede even as we fall towards them, our peculiar velocity merely reducing the rate at which the distance grows. Yet the Great Attractor, for all its gravitational influence, represents only a single node in a far more extensive architecture. Pull back further still, to scales where even superclusters become mere points of light, and a new pattern emerges. One that reveals the universe not as a random scattering of matter, but as an intricate network of thread-like structures stretching across billions of light-years. These are the cosmic filaments, the largest coherent structures in existence, and they form the skeleton upon which all visible matter hangs. The filaments appear in every deep survey of the universe, unmistakable once the data accumulates. They are not uniform columns of matter, but elongated concentrations, typically spanning 50 to 200 megaparsecs in length, 160 to 650 million light-years, while measuring only 5 to 10 megaparsecs across. This extreme aspect ratio, sometimes exceeding 20 to 1, gives them their thread-like appearance in three-dimensional maps. The Perseus-Pisces supercluster chain extends across nearly 300 million light-years, connecting multiple galaxy clusters like pearls on a cosmic string. The sculptor wall stretches even further, a sheet-like concentration of galaxies that spans much of the southern sky when viewed from our position in space. The physics that creates these structures begins with the same gravitational instability that forms clusters, but operating along different geometric constraints. In the early universe, matter was distributed with tiny density variations, regions slightly denser than average, and regions slightly emptier. As gravity amplified these variations over billions of years, the densest regions collapsed first, forming compact structures. But between these collapsing nodes, matter experienced competing gravitational pulls, drawn toward multiple centers simultaneously. Along the axes connecting dense regions, this competition resolved into elongated flows, with matter streaming along these corridors toward the nodes at either end. The mathematics of this process, first described in detail by Soviet physicist Yakov Zeldovich in the 1970s, predicts exactly the structures we observe. Zeldovich showed that gravitational collapse in 3 dimensions proceeds hierarchically. First, matter collapses along one axis to form sheet-like structures called walls or pancakes. Then these sheets collapse along a second axis to form filaments. Finally, filaments drain into nodes where clusters form. This Zeldovich pancake model explains why the cosmic web contains all 3 geometric elements: nodes, filaments, and walls, with filaments representing an intermediate stage in the ongoing collapse of matter. The density within filaments varies considerably, but typically exceeds the cosmic average by factors of 5 to 30. In concrete terms, while the average density of the universe is approximately 1 atom per 4 cubic meters, filament interiors contain perhaps 10 to 50 atoms in the same volume. This may seem negligible by terrestrial standards, still a vacuum far more perfect than anything achievable in laboratories, but it represents a significant overdensity by cosmic measures. This enhanced density means that galaxies within filaments experience more frequent interactions, more opportunities for gas accretion, and different evolutionary paths than their counterparts in emptier regions. The gas within filaments exists in a state that astronomers call the warm-hot intergalactic medium, or WHIM. Unlike the 100 million degree plasma in cluster cores, this filamentary gas maintains temperatures between 100,000 and 10 million Kelvin, hot enough to be ionized, too cool to emit detectable X-rays in most cases. Theoretical models predict that 30 to 40% of all ordinary matter in the universe resides in this warm-hot phase, making filaments the largest reservoir of baryonic matter outside of galaxies and clusters. Yet detecting this gas directly has proven extraordinarily difficult. It emits weakly and absorbs only specific wavelengths of light from background sources. Recent observations have begun to confirm these predictions. In 2019, astronomers using the XMM Newton Space Telescope detected X-ray emission from a filament connecting the galaxy clusters Abell 222 and Abell 223, measuring gas temperatures of approximately 20 million Kelvin and densities roughly 200 times the cosmic average. This detection, while representing an unusually dense and hot filament, demonstrated that the predicted structures do exist and contain the expected quantities of matter. Similar detections have followed, each adding to our census of the cosmic web's baryonic content. The filaments do not merely contain matter passively. They actively channel it toward the clusters at their intersections. Simulations reveal that galaxies within filaments move preferentially along the filament axis, flowing toward the nearest cluster node at velocities of several hundred kilometers per second. This streaming motion means that clusters grow not by accreting matter uniformly from all directions, but by feeding from the filaments that connect to them. A rich cluster like Coma, sitting at the intersection of multiple filaments, receives a continuous supply of galaxies and gas from these cosmic highways, while clusters in less connected positions grow more slowly. The geometry of filament connections follows patterns that reflect the underlying dark matter distribution. Most clusters connect to between 3 and 6 major filaments, with the exact number depending on the cluster's mass and its position within the larger web. The most massive clusters, those exceeding 10 to the 15th solar masses, tend to sit at the intersections of the most prominent filaments, their extreme mass a consequence of their privileged position in the network. Less massive clusters may connect to only 1 or 2 filaments, limiting their growth potential and ensuring they remain secondary structures in the cosmic hierarchy. Within the filaments themselves, galaxies are not distributed uniformly, but show their own substructure. Groups of galaxies, collections of 10 to 50 members bound by their mutual gravity, populate the filaments like beads along a wire. These groups represent the intermediate scale between individual galaxies and the massive clusters at filament intersections. The local group, containing the Milky Way and Andromeda among its 50-odd members, is itself embedded within a filament that connects toward the Virgo cluster, our nearest major cluster at a distance of 54 million light-years. The orientations of galaxies within filaments reveal the influence of these structures on galactic evolution. Studies of hundreds of thousands of galaxies show that spiral galaxies tend to align their rotation axes perpendicular to the filament direction, while elliptical galaxies show their major axes parallel to the filament. This alignment suggests that the tidal forces exerted by the filament's elongated mass distribution influence how galaxies form and evolve, imprinting the geometry of the cosmic web onto the shapes of individual stellar systems. The filaments also affect the properties of the galaxies they contain. Compared to galaxies in the emptiest voids, filament galaxies show higher rates of star formation, more frequent interactions with neighbors, and a greater tendency toward elliptical morphologies as one approaches the cluster nodes. This gradient in galaxy properties, from actively star-forming spirals in the outer filaments to quiescent ellipticals near cluster centers, reflects the increasing density of the environment and the accumulated effects of billions of years of gravitational processing. The longest filaments stretch across scales that challenge our ability to map them completely. The Sloan Great Wall, discovered in 2003 using data from the Sloan Digital Sky Survey, extends approximately 1.4 billion light-years across the northern sky, making it one of the largest known structures in the observable universe. Yet even this immense feature represents just one strand in the cosmic web, one thread among countless others that together form the universe's large-scale architecture. The filaments connect, branch, and merge across the observable universe, creating a network whose full extent we are only beginning to comprehend. Within this vast network of filaments and voids, a subtle pattern repeats itself across the cosmos, a signature so faint that it took decades of careful observation to detect, yet so fundamental that it echoes from the earliest moments of cosmic history. This pattern appears as a slight preference in the distances between galaxies, a statistical tendency for matter to cluster at particular separations rather than others. The scale of this preference measures approximately 490 million light-years, and its origin lies not in gravity alone, but in sound waves that traveled through the infant universe nearly 14 billion years ago. In the first 400,000 years after the Big Bang, the universe existed in a state utterly unlike anything we observe today. Matter and radiation were locked together in a dense, opaque plasma, with temperatures exceeding 3,000 Kelvin throughout. Photons could not travel freely through this primordial soup. Instead, they scattered constantly off free electrons, bouncing from particle to particle like light diffusing through fog. This coupling between matter and radiation created something remarkable, a medium through which pressure waves could propagate, much like sound waves traveling through air. But these were not ordinary sound waves. They were acoustic oscillations on cosmic scales, rippling through a plasma that filled the entire observable universe. The seeds of these oscillations lay in quantum fluctuations from the epoch of cosmic inflation, tiny variations in density that inflation stretched to astronomical scales. Where the density was slightly higher, gravity began pulling matter inward, compressing the plasma and raising its temperature. But this compression also increased the radiation pressure, which pushed back against gravity's pull. The result was oscillation, regions of the universe expanding and contracting in a cosmic rhythm, with matter and radiation sloshing back and forth together. The speed of these sound waves reached approximately 170,000 kilometers per second, or roughly 57% of the speed of light, far faster than any sound wave in the universe today. These acoustic oscillations continued for nearly 400,000 years, with pressure waves propagating outward from each initial overdensity, like ripples spreading from stones dropped into a pond. But unlike ripples in water, which continue spreading indefinitely, these cosmic sound waves had a finite lifetime. As the universe expanded and cooled, it approached a critical threshold, the moment when the temperature dropped below approximately 3,000 Kelvin and electrons could finally combine with protons to form neutral hydrogen atoms. This transition, called recombination, fundamentally changed the nature of the universe. Neutral atoms no longer scattered photons efficiently, and the coupling between matter and radiation suddenly broke. The universe became transparent, releasing the light that we now observe as the cosmic microwave background. At the moment of recombination, the sound waves froze. Without radiation pressure to sustain them, the oscillations ceased, but the pattern they had created remained imprinted in the distribution of matter. Each initial overdensity now sat at the center of a spherical shell of slightly enhanced density, located at the distance that sound waves had traveled during those first 400,000 years, a distance of approximately 150 megaparsecs, or 490 million light-years in today's expanded universe. This characteristic scale, known as the sound horizon, became permanently encoded in the cosmic matter distribution. The physics of this imprinting follows from the behavior of the oscillations at the moment they froze. Some regions of the universe were caught at maximum compression, where matter had piled up at the peaks of the sound waves. Others were caught at maximum rarefaction, where matter had spread thin in the troughs. But the most significant feature was the spherical shell around each initial overdensity, marking the distance that the leading edge of the sound wave had traveled before recombination. This shell contained a slight excess of matter compared to random locations at other distances, not a dramatic enhancement, but a statistical preference of roughly 1%. Over the following billions of years, gravity amplified these subtle density variations into the structures we observe today. Galaxies formed preferentially in regions of enhanced density, including both the original overdensities and the shells surrounding them. The result is a slight statistical tendency for galaxies to be separated by distances related to the sound horizon scale. When astronomers measure the distances between millions of galaxy pairs and plot the distribution, they find a small but unmistakable bump at approximately 490 million light-years. The baryon acoustic oscillation signal, a fossil record of sound waves that fell silent nearly 14 billion years ago. Detecting this signal required surveys of unprecedented scale and precision. The Sloan Digital Sky Survey, which began observations in 2000, mapped the positions of over 1 million galaxies across a significant fraction of the sky. In 2005, analysis of this data revealed the first clear detection of the baryon acoustic oscillation feature in the galaxy distribution, confirming theoretical predictions that had been made decades earlier. The measurement matched the scale predicted from observations of the cosmic microwave background with remarkable accuracy, providing powerful evidence that our understanding of the early universe rests on solid foundations. The baryon acoustic oscillation scale serves as what cosmologists call a standard ruler, a feature of known physical size that can be used to measure cosmic distances. Because we understand the physics that determined the sound horizon, we can calculate its true size with high precision. By measuring how large this feature appears at different distances, how the characteristic separation between galaxies changes with redshift, astronomers can map the expansion history of the universe. This technique has become one of the most powerful tools for studying dark energy, the mysterious component that drives the accelerating expansion of the cosmos. The precision of baryon acoustic oscillation measurements continues to improve as surveys grow larger. The Dark Energy Spectroscopic Instrument, which began full operations in 2021, aims to measure the positions of over 30 million galaxies and quasars, extending the baryon acoustic oscillation measurements to earlier cosmic epochs with unprecedented accuracy. Each new measurement constrains the properties of dark energy more tightly, testing whether its density remains constant over time or evolves in ways that might reveal its fundamental nature. The baryon acoustic oscillation signal also appears in the cosmic microwave background itself, manifesting as a series of peaks in the temperature fluctuation spectrum. These peaks correspond to different harmonics of the acoustic oscillations, the fundamental mode and its overtones frozen at the moment of recombination. The first peak, at an angular scale of approximately 1 degree on the sky, corresponds to regions that had completed exactly half an oscillation by the time of recombination, caught at maximum compression. The second peak corresponds to regions that had completed a full oscillation, caught at maximum rarefaction. The precise positions and heights of these peaks encode information about the composition and geometry of the universe, allowing cosmologists to measure parameters like the total matter density and the curvature of space with percent-level precision. The relationship between the peaks in the cosmic microwave background and the bump in the galaxy distribution reflects the same underlying physics viewed at different epochs. The microwave background shows us the acoustic oscillations at the moment they froze, while the galaxy distribution shows us how those frozen patterns evolved under gravity over the subsequent billions of years. The consistency between these two measurements, the fact that they yield compatible values for cosmological parameters, represents one of the great triumphs of modern cosmology, demonstrating that our theoretical framework accurately describes the universe from its earliest moments to the present day. Yet the baryon acoustic oscillation signal carries information beyond simple distance measurements. The way the signal appears slightly different along the line of sight compared to across the sky, a phenomenon called the Alcock-Podzinski effect, provides additional constraints on cosmic geometry. The amplitude of the signal and how it changes with redshift reveals information about the growth rate of cosmic structure, testing whether gravity behaves as general relativity predicts on the largest scales. Each aspect of the baryon acoustic oscillation feature offers a different window into fundamental physics. The sound waves that created this pattern traveled through a universe vastly different from today's, a universe filled with plasma rather than atoms, where light and matter moved as one. Those waves fell silent nearly 14 billion years ago, yet their echo persists in the arrangement of galaxies across the sky, a frozen record of cosmic acoustics written in the positions of 100 billion galaxies. The filaments and clusters that define the cosmic web carry this ancient signature within their distribution, a subtle statistical preference that reveals the universe once rang with sound. That frozen acoustic signature, imprinted in the distribution of luminous matter, traces only a fraction of the true architecture. For every galaxy cluster that glows with starlight, for every filament traced by the positions of visible galaxies, a far more massive structure exists in darkness, unseen, unlit, yet utterly dominant in shaping the cosmos. The cosmic web that spans the observable universe is not primarily a web of stars and gas. It is a web of dark matter, and everything we can see merely decorates its invisible scaffolding. The evidence for this hidden framework accumulated gradually across the 20th century, beginning with observations that seemed, at first, to be simple measurement errors. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster, measuring the velocities of individual galaxies as they orbited within the cluster's gravitational embrace. The results defied explanation. The galaxies moved far too quickly, velocities exceeding 1,000 kilometers per second, to remain bound by the gravitational pull of the visible matter alone. By Zwicky's calculations, the cluster required roughly 400 times more mass than the stars could provide. He called this missing component Dunkelmaterie, dark matter, and for decades the astronomical community largely ignored his conclusion. The problem resurfaced in the 1970s when Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies with unprecedented precision. In a galaxy governed only by visible matter, stars in the outer regions should orbit more slowly than those near the center, just as Neptune moves more sluggishly around the Sun than Mercury does. Instead, Rubin and Ford found that rotation speeds remained nearly constant, far beyond where the visible disk faded into darkness. The Andromeda Galaxy, for instance, shows rotation velocities of approximately 225 kilometers per second, extending well past 50,000 light-years from its center, where almost no visible matter remains. The only explanation that fit the data was a vast halo of invisible mass surrounding each galaxy, extending far beyond the luminous disk and containing 5 to 10 times more matter than all the stars combined. Today, cosmologists estimate that dark matter constitutes approximately 27% of the universe's total energy content, compared to just 5% for ordinary baryonic matter, the protons, neutrons, and electrons that compose stars, planets, and human bodies. The remaining 68% belongs to dark energy, but that mysterious component influences only the universe's expansion rate, not the formation of structure. When it comes to building the cosmic web, dark matter dominates absolutely. It provides the gravitational skeleton upon which all visible structure hangs. The nature of dark matter remains one of physics' deepest mysteries, but its behavior is well constrained by observation. It interacts gravitationally, pulling on ordinary matter and on itself. It does not interact electromagnetically, meaning it neither emits nor absorbs light at any wavelength. It does not participate in the strong nuclear force that binds atomic nuclei. Whether it interacts through the weak nuclear force remains an open question, one that particle physicists probe with detectors buried deep underground, shielded from cosmic rays, waiting for the rare collision between a dark matter particle and an atomic nucleus. So far, no confirmed detection has occurred, despite decades of searching with increasingly sensitive instruments. What cosmologists do know is how dark matter behaves on large scales, and this behavior explains the cosmic web's architecture with remarkable precision. In the early universe, dark matter was distributed almost uniformly, with density variations of only 1 part in 100,000. These tiny fluctuations, seeded during cosmic inflation, provided the initial conditions for everything that followed. Where dark matter was slightly denser, its gravitational pull attracted more matter from surrounding regions. Where it was slightly less dense, matter flowed away toward denser areas. This process of gravitational instability, operating over billions of years, amplified the initial fluctuations into the dramatic contrasts we observe today. Computer simulations have traced this evolution in extraordinary detail. The Millennium simulation, completed in 2005, followed the gravitational interactions of 10 billion dark matter particles within a cubic volume 2.4 billion light-years on each side, tracking structure formation from redshift 127, roughly 50 million years after the Big Bang, to the present day. More recent simulations, like Illustri's TNG, incorporate not just dark matter but also gas physics, star formation, and supermassive black hole feedback, modeling the interplay between visible and invisible matter across cosmic time. These simulations consistently produce the same basic architecture, a network of dense filaments connecting massive nodes surrounding vast empty voids, with sheets of moderate density forming the boundaries between different void regions. The filaments emerge naturally from gravitational dynamics. When matter collapses under its own gravity, it does not fall inward symmetrically from all directions. Instead, collapse proceeds fastest along the shortest axis, causing initially spherical overdensities to flatten into sheets. These sheets then collapse further along their second shortest axis, producing elongated filaments. Only at the intersections of multiple filaments does matter finally collapse along all three axes to form the dense, roughly spherical halos that host galaxy clusters. This hierarchical collapse explains why filaments are so ubiquitous. They represent an intermediate stage in the gravitational processing of matter, more evolved than sheets, but not yet compressed into nodes. Within this dark matter web, ordinary baryonic matter follows like a passenger. Gas falls into the gravitational potential wells carved by dark matter, accumulating in halos and along filaments. Where gas density exceeds critical thresholds, it cools, fragments, and collapses further to form stars and galaxies. The galaxies we observe thus trace the underlying dark matter distribution. Though imperfectly, baryonic physics introduces complications that pure gravitational simulations cannot capture. Supernova explosions drive gas out of small galaxies, active galactic nuclear heat surrounding gas, and suppress star formation in massive systems. These feedback processes modify the relationship between dark and luminous matter, making galaxies biased tracers of the true mass distribution. Gravitational lensing provides the most direct method for mapping dark matter's invisible scaffolding. When light from distant galaxies passes near a massive foreground structure, gravity bends its path, distorting the images of background sources. Strong lensing produces dramatic arcs and multiple images around galaxy clusters, while weak lensing creates subtle statistical alignments in the shapes of millions of background galaxies. By measuring these distortions across large areas of sky, cosmologists can reconstruct the total mass distribution regardless of whether that mass emits light. The resulting maps reveal dark matter filaments stretching between clusters, confirming that the cosmic web exists not just in simulations, but in the actual universe. One particularly striking example connects the galaxy clusters Abell 222 and Abell 223, separated by approximately 400 million light-years. Weak lensing observations revealed a filament of dark matter bridging the two clusters, containing mass equivalent to roughly 9 trillion suns distributed along a structure 65 million light-years long. Hot gas detected through X-ray emission traces the same filament, heated to tens of millions of degrees as it falls into the dark matter's gravitational potential. This single observation encapsulates the cosmic web's essential nature. Dark matter provides the gravitational framework, and baryonic matter follows, lighting up only a small fraction of the total structure. The halos that host individual galaxies nest within larger halos that host galaxy groups, which themselves reside within still larger halos encompassing clusters. This hierarchy of nested structures reflects the bottom-up nature of cosmic structure formation in a universe dominated by cold, dark matter. Dark matter particles that moved slowly compared to the speed of light when the universe was young, allowing small-scale structures to form first and merge into progressively larger systems. A galaxy like the Milky Way sits within a dark matter halo, extending roughly 1 million light-years from the galactic center, containing approximately 1 trillion solar masses of invisible matter. This halo is not smooth, but contains substructure, smaller halos that survived the merging process, some hosting dwarf satellite galaxies, others remaining entirely dark. The cosmic web thus represents dark matter's ultimate architectural achievement, a structure spanning hundreds of millions of light-years, yet built from the gravitational interactions of particles whose individual nature remains unknown. Every galaxy cluster, every filament, every void boundary exists because dark matter's gravity shaped the universe's evolution from almost perfect uniformity to the rich complexity we observe today. The visible cosmos, all the stars, all the galaxies, all the glowing gas, amounts to a thin, luminous frosting on an invisible cake, tracing patterns determined by matter we cannot see, touch, or directly detect, yet whose gravitational influence governs the largest structures in existence. And yet, for all the gravitational artistry that dark matter has woven through the cosmos, the most striking features of the cosmic web are not the structures themselves, but the absences between them. The voids, those vast, nearly empty regions that occupy the majority of the universe's volume, represent something profound. The places where gravity lost its ancient competition with cosmic expansion, where matter fled outward toward denser regions, leaving behind spherical caverns of almost unimaginable emptiness. These cosmic voids are not merely gaps between structures. They are structures in their own right, defined by their boundaries, shaped by their own peculiar physics, and responsible for much of the universe's large-scale organization. If the filaments and clusters represent the bones and joints of the cosmic skeleton, then the voids are the spaces those bones protect. Vast chambers that together comprise roughly 80% of the universe's total volume, yet contain perhaps only 10 to 20% of its matter. The physics of void formation begins in the same primordial density fluctuations that seeded galaxy clusters and filaments. In the early universe, regions of slightly below average density existed alongside the overdense patches that would eventually collapse into structures. But while overdense regions attracted more matter through gravitational pull, underdense regions experienced the opposite fate. Matter within these sparse zones felt stronger gravitational attraction towards the denser surroundings than towards the void centers. Slowly, inexorably, particles migrated outward, evacuating the underdense regions and accumulating along their boundaries. This evacuation process, operating over billions of years, transformed modest density deficits into profound emptiness. A region that began with perhaps 5% less matter than average could, through this gravitational drainage, become a void containing only 1/10 the cosmic mean density. The matter that once occupied these spaces now resides in the walls, filaments, and clusters that define void boundaries, structure and emptiness creating each other through the same gravitational physics. The Boötes void, discovered in 1981, provided one of the first dramatic illustrations of this cosmic emptiness. Spanning approximately 330 million light-years in diameter, this roughly spherical region contains so few galaxies that astronomers initially questioned their observations. Within a volume that should statistically contain roughly 2,000 galaxies, the Boötes void holds only 60, a density deficit so extreme that early researchers wondered if observational errors or dust obscuration might explain the apparent emptiness. Subsequent surveys confirmed the void's reality. This region of space is genuinely, profoundly underpopulated. Yet the Boötes void, for all its impressive scale, represents only a modest example of cosmic emptiness. The KBC void, named after astronomers Keenan, Barger, and Cowie, who characterized it in 2013, may extend across 2 billion light-years, potentially making it one of the largest known structures in the observable universe. Our own Milky Way appears to reside within this vast underdensity, which could explain certain anomalies in measurements of the local expansion rate. If we inhabit a region where matter density falls roughly 20% below the cosmic average, the local expansion of space would proceed slightly faster than in denser environments, a subtle effect that might account for some of the tension between different methods of measuring the Hubble constant. The average density within cosmic voids hovers around 1 atom per 10 cubic meters, roughly 1/10 the already sparse cosmic mean of 1 atom per cubic meter. To appreciate this emptiness, consider that the best laboratory vacuums on Earth contain approximately 100 billion molecules per cubic centimeter. Interstellar space within our galaxy holds roughly 1 atom per cubic centimeter. But the deep interiors of cosmic voids achieve densities 1,000,000 times lower still, approaching the most perfect vacuums that nature permits on large scales. This near emptiness does not mean voids are entirely devoid of structure. Careful surveys reveal that even within these sparse regions, matter organizes itself into tenuous networks. Void galaxies, those rare systems that inhabit the interior regions rather than the walls, tend to be smaller, bluer, and more actively forming stars than their counterparts in denser environments. Isolated from the gravitational harassment and gas-stripping processes common in clusters, these void dwellers evolve in relative peace, their star formation proceeding at leisurely rates dictated only by their own internal gas supplies. The shapes of voids revealed the physics of their formation. Younger, smaller voids tend toward spherical geometry, their boundaries expanding outward at roughly equal rates in all directions. But as voids grow and merge, they develop more complex shapes. Elongated ellipsoids, irregular polyhedra defined by the filaments and walls that bound them. The largest voids often result from the merger of smaller predecessors, their boundaries marked by the remnant walls of formerly separate empty regions. Void expansion occurs not through the physical motion of their boundaries, but through the continued evacuation of matter from their interiors. Galaxies near void centers experience net gravitational attraction toward the denser walls, causing them to drift outward at velocities of several hundred kilometers per second. This peculiar velocity field, the systematic motion of matter away from void centers, provides one method for mapping void geometry, even when the voids themselves contain too few galaxies for direct observation. The walls between voids, where matter accumulates after draining from the empty regions, achieve densities roughly twice the cosmic average. These walls, typically 10 to 20 million light-years thick, host the majority of galaxies in the universe. Most spiral galaxies, including our own Milky Way, reside in such wall environments, neither in the densest cluster cores nor in the emptiest void interiors, but in the moderate density boundaries that separate cosmic emptiness from cosmic emptiness. Temperature within voids differs subtly from the cosmic mean. With less matter to gravitationally heat the sparse intergalactic medium, void interiors remain slightly cooler than the gas in denser regions. The temperature difference amounts to only a few percent, perhaps 10,000 Kelvin versus 11,000 Kelvin. But this thermal signature provides another tool for mapping void distributions across cosmic distances. The void hierarchy extends across multiple scales. The smallest voids, sometimes called mini-voids, span only 10 to 20 million light-years and often nest within the walls of larger structures. Medium-sized voids, like the local void adjacent to our own galaxy, extend 100 to 200 million light-years. The largest supervoids, such as the cold spot supervoid potentially associated with an anomalous region in the cosmic microwave background, may reach 500 million light-years or more. Structures so vast that light requires 500 million years to traverse them. This local void, discovered through careful mapping of galaxy distributions in our cosmic neighborhood, lies adjacent to the Virgo supercluster and influences the motion of our own galaxy. The Milky Way moves not only toward the great attractor but also away from the local void, pushed by the relative absence of gravitational attraction from that empty direction. This void repulsion, combined with the attraction toward overdense regions, shapes the complex velocity field of our local cosmic environment. Dark energy, the mysterious force accelerating cosmic expansion, finds its most dramatic expression within voids. In these underdense regions, where matter's gravitational braking effect is weakest, dark energy's repulsive influence dominates most completely. Voids expand faster than the cosmic average, their boundaries pushed outward by the accelerating expansion of space itself. Over billions of years, this differential expansion will cause voids to grow, while clusters and filaments maintain their gravitationally bound integrity. The universe becoming increasingly dominated by emptiness as cosmic time advances. The statistics of void sizes and distributions encode information about fundamental cosmological parameters. The abundance of voids of different sizes depends sensitively on the total matter density, the amplitude of primordial fluctuations, and the properties of dark energy. By carefully cataloging voids across large survey volumes, measuring their sizes, shapes, and spatial distributions, Cosmologists extract constraints on these parameters that complement and cross-check measurements from other methods. Simulations of cosmic structure formation reproduce the observed void hierarchy with remarkable fidelity. The Millennium simulation and its successors generate void populations whose statistical properties match observations. The right distribution of sizes, the correct density profiles from void centers to walls, the appropriate shapes and clustering patterns. This agreement confirms that our understanding of gravitational physics, applied to the initial conditions revealed by the cosmic microwave background, correctly predicts the emergence of cosmic emptiness alongside cosmic structure. The boundaries between voids and the surrounding cosmic web are not sharp edges, but gradual transitions. Density increases smoothly from void centers outward, following profiles that cosmologists describe with mathematical functions calibrated against both simulations and observations. The transition zone, where void interior gives way to wall environment, extends across tens of millions of light years, a gradual slope rather than a cliff edge. These gradual transitions, where emptiness yields to structure across vast distances, reveal themselves most dramatically when astronomers map the universe at its largest observable scales. For it is at these scales, spanning hundreds of millions to billions of light years, that the cosmic web assembles into configurations so immense that they challenge our very definitions of cosmic structure. The Sloan Great Wall stands as one of the most thoroughly documented of these configurations. Discovered in 2003 through data from the Sloan Digital Sky Survey, this enormous arrangement of galaxies stretches approximately 1.37 billion light-years across the northern sky. To place this distance in perspective, light departing from one end of the Sloan Great Wall, when complex life first emerged on Earth, would still have more than 1 billion years of travel remaining before reaching the opposite end. The structure contains hundreds of thousands of galaxies organized into a flattened, wall-like configuration that traces the boundaries between multiple cosmic voids. The Sloan Digital Sky Survey that revealed this structure represents one of humanity's most ambitious cartographic endeavors. Using a dedicated 2.5-meter telescope at Apache Point Observatory in New Mexico, the survey measured the positions and redshifts of more than 3 million galaxies across 1/4 of the entire sky. Each redshift measurement, the stretching of light toward longer wavelengths caused by cosmic expansion, provides a distance estimate, transforming two-dimensional sky positions into three-dimensional cosmic maps. The Sloan Great Wall emerged from these maps as a clear overdensity, a region where galaxy counts significantly exceed the cosmic average. This wall-like structure sits at a redshift of approximately 0.08, corresponding to a distance of roughly 1 billion light-years from Earth. Its discovery demonstrated that the cosmic web's filamentary architecture extends to scales far larger than the superclusters astronomers had previously catalogued. The Sloan Great Wall is not a single coherent object bound by gravity, but rather a chance alignment of multiple superclusters and filaments that together create the appearance of a continuous wall when viewed from our particular vantage point in the cosmos. The individual components of the Sloan Great Wall include several well-known galaxy concentrations. The Shapley supercluster, one of the most massive structures in the nearby universe, contributes to the wall's overall extent. With a mass estimated at approximately 10 million billion solar masses, Shapley alone contains more than 24 rich galaxy clusters, each hosting hundreds to thousands of member galaxies. The gravitational influence of such concentrations extends across hundreds of millions of light-years, drawing surrounding matter into the wall-like configuration. Yet even the Sloan Great Wall pales before structures detected at greater distances. In 2013, astronomers announced the discovery of the Hercules Corona Borealis Great Wall, a structure so vast that it stretched the boundaries of what cosmologists considered physically possible. Spanning an estimated 10 billion light-years, more than 7 times the length of the Sloan Great Wall, this configuration appeared in maps of gamma-ray bursts, the most energetic explosions in the universe. Gamma-ray bursts serve as cosmic beacons, their extreme luminosity visible across billions of light-years. When massive stars collapse or neutron stars merge, they release bursts of gamma radiation that outshine entire galaxies for brief moments. By cataloging the positions and distances of these bursts, astronomers can trace the distribution of matter at redshifts where ordinary galaxy surveys struggle to penetrate. The Hercules Corona Borealis Great Wall revealed itself as a statistically significant clustering of gamma-ray bursts between redshifts of 1.6 and 2.1, corresponding to distances between roughly 10 and 11 billion light-years. The existence of such an enormous structure raises profound questions about cosmic homogeneity. The cosmological principle, the assumption that the universe appears roughly the same in all directions when viewed at sufficiently large scales, predicts that structures should not exceed certain size limits. Theoretical calculations suggest that the transition to homogeneity should occur at scales around 300 to 400 megaparsecs, roughly 1 billion light-years. Structures significantly larger than this scale would violate the statistical uniformity that underlies our standard cosmological models. The Hercules Corona Borealis Great Wall, if confirmed as a genuine coherent structure, would exceed this homogeneity scale by nearly an order of magnitude. Some cosmologists argue that the apparent structure may result from observational biases or statistical fluctuations in the gamma-ray burst data, rather than a true physical concentration of matter. The relatively small number of gamma-ray bursts available for analysis, fewer than 500 in the relevant redshift range, makes definitive conclusions challenging. Other astronomers point to additional large-scale structures that similarly push against homogeneity limits. The huge large quasar group, discovered in 2013, spans approximately 4 billion light-years and contains 73 quasars clustered together at a redshift of 1.27. Quasars, the brilliant cores of galaxies powered by supermassive black holes consuming surrounding matter, serve as distance markers similar to gamma-ray bursts. Their clustering into such an extended configuration suggests that the cosmic web may indeed organize matter into arrangements larger than standard models predict. The giant arc, announced in 2021, adds further evidence for extreme-scale structure. This crescent-shaped arrangement of galaxies spans 3.3 billion light-years at a redshift of 0.8, making it visible in the same region of sky as the huge large quasar group. The probability of such a configuration arising by chance in a statistically homogeneous universe is less than 1 in 10,000, suggesting either genuine physical structure or unknown systematic effects in the observations. These discoveries have prompted cosmologists to reconsider the scale at which cosmic homogeneity truly emerges. Perhaps the transition occurs at larger scales than previously assumed, or perhaps the universe contains rare statistical outliers that do not violate the cosmological principle when averaged over sufficiently large volumes. The debate continues, with each new survey adding data points that either confirm or challenge our understanding of cosmic architecture. The physical mechanisms that could create such enormous structures remain subjects of active research. Gravitational collapse alone cannot explain configurations spanning billions of light-years. The universe is simply not old enough for gravity to have drawn matter together across such distances. Instead, these structures likely trace primordial density variations imprinted during cosmic inflation, the exponential expansion that occurred in the universe's first fraction of a second. Inflation stretched quantum fluctuations to cosmic scales, creating regions of slightly higher and lower density that would later seed the formation of all structure. If inflation produced fluctuations with particular statistical properties, perhaps slight deviations from the expected Gaussian random distribution, these could manifest as unexpectedly large structures in the present-day universe. The Hercules corona borealis, Great Wall, and similar configurations may thus provide windows into physics that occurred when the observable universe was smaller than an atomic nucleus. The walls themselves, regardless of their ultimate interpretation, demonstrate the hierarchical nature of cosmic structure. Just as galaxies cluster into groups, groups into clusters, and clusters into superclusters, so too do superclusters arrange themselves into walls and filaments that bound the largest voids. Each scale reveals patterns that emerge from the same underlying physics: gravitational attraction amplifying primordial density contrasts, operating across different distance and time scales. Mapping these structures requires surveys of ever-increasing scope. The Dark Energy Spectroscopic Instrument, currently operating at Kitt Peak National Observatory, aims to measure redshifts for 40 million galaxies and quasars, creating the most detailed three-dimensional map of the universe ever assembled. The Euclid Space Telescope, launched in 2023, will survey 15,000 square degrees of sky, cataloging billions of galaxies out to redshifts of 2 and beyond. These instruments will either confirm the existence of structures exceeding the homogeneity scale, or reveal that current detections result from observational artifacts. The walls and voids that these surveys reveal are not static configurations, but dynamic systems evolving under the competing influences of gravity and cosmic expansion. Dark energy, the mysterious force accelerating the universe's expansion, gradually weakens the gravitational bonds that hold structures together. Over billions of years, the walls will stretch, the filaments will thin, and the voids will expand, slowly erasing the intricate architecture that gravity has spent cosmic history constructing. Understanding how these structures evolve, how walls stretch and voids expand under dark energy's relentless push, requires first knowing where everything is. And that knowledge comes from one of astronomy's most painstaking endeavors: the systematic measurement of distance to billions of individual galaxies scattered across the observable universe. The challenge is deceptively simple to state, but monumentally difficult to execute. Light from a distant galaxy carries information about that galaxy's motion through space, encoded in the precise wavelengths of its spectral lines. When a galaxy moves away from us, those wavelengths stretch toward the red end of the spectrum, a phenomenon called redshift. The faster the recession, the greater the stretch. And because the universe expands uniformly at large scales, a galaxy's redshift directly indicates its distance. A galaxy with a redshift of 0.1 lies roughly 1.3 billion light-years away, while one at redshift 1.0 sits approximately 7.7 billion light-years distant, its light having traveled for more than half the universe's current age. But measuring a single galaxy's redshift requires capturing enough of its light to spread into a spectrum, identifying the characteristic emission or absorption lines of elements like hydrogen, oxygen, and calcium, then calculating how far those lines have shifted from their laboratory wavelengths. For a bright nearby galaxy, this might take minutes of telescope time. For a faint smudge at the edge of detectability, it might require hours. Multiply this by the hundreds of millions of galaxies visible to modern instruments, and the scale of the mapping problem becomes clear. The first systematic attempt to chart the three-dimensional universe began in the 1980s with the CFA Redshift Survey, which measured distances to approximately 2,400 galaxies in a slice of sky. Even this modest sample revealed something unexpected. Galaxies were not scattered randomly through space, but clustered along walls and filaments surrounding vast empty regions. The discovery of the Great Wall, a sheet of galaxies stretching 500 million light-years across, demonstrated that structure existed at scales far larger than anyone had anticipated. The Sloan Digital Sky Survey, beginning observations in 2000, transformed this trickle of data into a flood. Using a dedicated 2.5-meter telescope at Apache Point Observatory in New Mexico, equipped with a camera containing 120 million pixels and spectrographs, capable of measuring 640 galaxy redshifts simultaneously, SDSS systematically photographed and analyzed 1/4 of the entire sky. Over 2 decades of operation, it has measured precise redshifts for more than 4 million galaxies and quasars, creating the most detailed three-dimensional map of the universe ever constructed. The technical innovations that made this possible seem almost mundane compared to the cosmic structures they revealed. Aluminum plates, drilled with hundreds of precisely positioned holes, allowed optical fibers to be plugged into exact locations corresponding to target galaxies. Light from each fiber fed into spectrographs that dispersed it into its component wavelengths. Software algorithms automatically identified spectral features and calculated redshifts with accuracies better than 30 kilometers per second, precise enough to distinguish a galaxy's peculiar motion from the overall cosmic expansion. The 2-degree Field Galaxy Redshift Survey, conducted from the Anglo-Australian Telescope between 1997 and 2002, took a complementary approach, measuring 221,414 galaxies across 2 strips of sky. Its robotic fiber positioner could reconfigure 400 optical fibers in under an hour, allowing efficient observation of dense galaxy fields. Together with SDSS, these surveys revealed the cosmic web in unprecedented detail. Filaments threading between clusters, walls extending for hundreds of megaparsecs, voids spanning 100 million light-years or more. Yet even these achievements represent only a fraction of the observable universe. The SDSS spectroscopic sample, vast as it is, covers galaxies out to redshifts of approximately 0.7, looking back roughly 6 billion years. Beyond this horizon, galaxies grow fainter and more numerous, their light stretched into infrared wavelengths that ground-based telescopes struggle to detect. Mapping the full depth of cosmic history requires different strategies. Photometric redshifts offer one solution. Instead of measuring detailed spectra, astronomers photograph galaxies through multiple colored filters, then use the resulting brightness measurements to estimate redshifts. A galaxy's color depends on the ages and types of its stars, and these colors shift predictably with distance. By comparing observed colors to templates, algorithms can estimate redshifts for millions of galaxies in the time it would take to measure spectra for thousands. The Dark Energy Survey, using a 570-megapixel camera on a 4-meter telescope in Chile, has catalogued 300 million galaxies using this technique, though with distance uncertainties roughly 10 times larger than spectroscopic measurements. The next generation of surveys will push these boundaries further still. The Dark Energy Spectroscopic Instrument, installed on the Mayol telescope at Kitt Peak, Arizona, began operations in 2021 with 5,000 robotic fiber positioners capable of reconfiguring in under 2 minutes. Over its 5-year primary mission, DESI will measure spectroscopic redshifts for 35 million galaxies and quasars, probing the universe's expansion history with unprecedented precision. Its targets include luminous red galaxies out to redshift 1.0, emission line galaxies to redshift 1.6, and quasars, the brilliant cores of distant galaxies powered by supermassive black holes, out to redshift 3.5 when the universe was less than 2 billion years old. The European Space Agency's Euclid mission, launched in 2023, will survey 15,000 square degrees of sky from orbit, free from atmospheric distortion. Its near-infrared spectrograph will measure redshifts for approximately 30 million galaxies, while its imaging cameras will capture the shapes of 1.5 billion galaxies for weak gravitational lensing studies. Combined with ground-based photometry, Euclid will map the distribution of matter, both visible and dark, across 10 billion years of cosmic history. The Vera C. Rubin Observatory, under construction in Chile, will take yet another approach. Its 8.4-meter primary mirror and 3.2 gigapixel camera, the largest digital camera ever built, will photograph the entire visible southern sky every 3 nights for 10 years. This legacy survey of space and time will detect 20 billion galaxies, measuring photometric redshifts for the vast majority. Though less precise than spectroscopic measurements, the sheer statistical power of billions of distance estimates will reveal subtle patterns in the cosmic web that smaller samples cannot detect. Each survey builds upon its predecessors, filling gaps in sky coverage, pushing to fainter magnitudes, reaching higher redshifts. The accumulated data now exceeds petabytes, millions of gigabytes of images, spectra, and derived measurements stored in databases accessible to astronomers worldwide. Machine learning algorithms, trained on millions of classified galaxies, now automatically identify and measure new objects faster than human experts ever could. What emerges from this torrent of data is a picture of the universe as a vast, interconnected network of matter, its structure encoded in the positions of billions of luminous traces. Statistical analyses reveal the characteristic scales of clustering. Galaxies separated by 5 megaparsecs are more likely to be found together than chance would predict, a correlation that weakens but persists out to separations of 150 megaparsecs, where Orion acoustic oscillation signal appears as a subtle excess. Beyond 300 megaparsecs, correlations fade to insignificance, and the universe approaches statistical homogeneity. The power spectrum, a mathematical tool that decomposes the galaxy distribution into contributions from different spatial scales, encodes this information precisely. Its shape reflects the physics of structure formation. The initial spectrum of density fluctuations from cosmic inflation, modified by the growth of perturbations under gravity, shaped by the acoustic oscillations in the early universe, and filtered by the complex processes of galaxy formation. Comparing observed power spectra to theoretical predictions constrains cosmological parameters with remarkable precision. The density of dark matter, the expansion rate, the amplitude of primordial fluctuations. These surveys have also revealed how structure evolves over cosmic time. Galaxies at high redshift cluster less strongly than nearby galaxies, reflecting the gradual amplification of density contrasts by gravity. The growth rate of structure depends sensitively on the properties of dark energy. If dark energy's influence strengthens over time, structure growth slows. If it weakens, clustering accelerates. Current measurements favor a cosmological constant, with dark energy density remaining fixed as space expands, though uncertainties remain large enough to accommodate alternative models. Yet for all the intricate structure these surveys reveal, the filaments and walls, the clusters and voids, the web-like patterns stretching across billions of light-years, a profound question emerges when astronomers step back far enough. At what scale does all this complexity dissolve into uniformity? At what distance do the cosmic web's elaborate patterns blur into a smooth, featureless expanse? This question lies at the heart of modern cosmology, for the entire theoretical framework that describes the universe's evolution rests on a fundamental assumption that on sufficiently large scales, the cosmos is homogeneous and isotropic. Homogeneous means the same everywhere. No special locations, no cosmic center, no preferred regions of higher or lower density. Isotropic means the same in every direction. No preferred axis, no cosmic north or south. Together, these properties form the cosmological principle, the bedrock assumption that allows physicists to apply the same equations of general relativity uniformly across all of space. The evidence for this principle, at first glance, seems contradictory. Look at the universe on the scale of a single galaxy, and you find matter concentrated into a disk perhaps 100,000 light-years across, surrounded by vast emptiness. Zoom out to galaxy clusters, and you see matter clumped into regions spanning 10 to 20 million light-years, separated by voids stretching 50 million light-years or more. The Sloan Great Wall extends across 1.4 billion light-years. The Hercules Corona Borealis Great Wall, if confirmed, might span 10 billion light-years. Where in all this lumpy structure does uniformity emerge? The answer comes from careful statistical analysis of galaxy distributions, and it arrives at a specific number, approximately 300 megaparsecs, or roughly 1 billion light-years. Below this scale, the universe remains decidedly inhomogeneous. Density fluctuations persist, with some regions containing twice the average matter density, while others hold barely a tenth. The cosmic web's filaments and voids dominate the landscape, creating patterns that repeat but never quite identically, like the branching of trees or the meandering of rivers. Above 300 megaparsecs, however, something remarkable occurs. The fluctuations begin to average out. A sphere of this radius centered on any random point in the universe contains, statistically speaking, the same amount of matter as a sphere of equal size centered anywhere else. The density contrast, the fractional difference between local density and the cosmic average, drops below 1%. The universe, viewed at this scale, becomes as smooth as a still pond. This transition from structure to uniformity follows mathematical patterns that cosmologists can predict from first principles. The power spectrum of density fluctuations, which describes how much clustering exists at each scale, decreases at larger wavelengths according to specific rules set by the physics of cosmic inflation and subsequent gravitational evolution. On scales smaller than the horizon at matter radiation equality, about 450 megaparsecs, the power spectrum rises toward smaller scales, meaning more structure exists at smaller sizes. On scales larger than this characteristic length, the spectrum flattens or even decreases, reflecting the primordial fluctuations generated during inflation, which possessed nearly equal amplitude at all scales. The transition to homogeneity can be quantified through a statistical measure called the correlation function, which describes the probability of finding a galaxy at a given distance from another galaxy compared to a random distribution. At small separations, a few megaparsecs, this correlation is strong, reflecting the tendency of galaxies to cluster together in groups and filaments. At separations of 100 megaparsecs, the correlation weakens but remains detectable, tracing the Baryon acoustic oscillation scale. Beyond 300 megaparsecs, the correlation function approaches zero, meaning galaxy positions become statistically independent. Finding a galaxy in one location tells you nothing about whether another galaxy exists 300 megaparsecs away. This homogeneity scale carries profound implications for cosmological measurements. When astronomers calculate the average density of the universe, currently measured at approximately 9.9 times 10 to the -27th kilograms per cubic meter, equivalent to about 6 hydrogen atoms per cubic meter. They must average over volumes large enough to encompass this transition. Smaller volumes yield wildly varying results, depending on whether they happen to contain a cluster or a void. Only by surveying regions exceeding 1 billion light-years across can reliable cosmic averages emerge. The homogeneity scale also sets limits on the largest possible structures. If the universe becomes statistically uniform above 300 megaparsecs, then no coherent structure should exist at significantly larger scales. This prediction creates tension with observations like the Hercules Corona Borealis Great Wall, whose claimed extent of 10 billion light-years would violate the cosmological principle if confirmed as a single gravitationally bound or coherently evolving structure. Most cosmologists suspect such apparent megastructures represent chance alignments or statistical flukes in galaxy distributions, rather than genuine physical entities. Though the question remains open pending more detailed surveys. The isotropy of the universe, its sameness in all directions, finds its most precise confirmation in the cosmic microwave background radiation. This ancient light, released when the universe was just 380,000 years old, arrives at Earth from every direction with a temperature of 2.7255 Kelvin, uniform to 1 part in 100,000. The tiny fluctuations that do exist at the level of a few hundred microkelvins trace the primordial density variations that would eventually grow into today's cosmic web. But the overwhelming uniformity of this radiation demonstrates that the early universe was extraordinarily homogeneous, with density contrasts of merely 0.001%. From that nearly perfect smoothness, gravity has amplified the fluctuations by a factor of roughly 100,000 over 13.8 billion years, creating the elaborate structures visible today. Yet this amplification operates within limits. Gravity can enhance existing density contrasts, but cannot create structure on scales larger than light could have traveled since the Big Bang. The observable universe spans approximately 93 billion light-years in diameter. But coherent gravitational structures cannot exceed a few billion light-years, because there simply has not been enough time for matter separated by greater distances to gravitationally influence each other. This causal limit reinforces the homogeneity scale from a different angle. Structures form through gravitational collapse, which requires matter to fall together over cosmic time. The maximum distance matter can have traveled since the Big Bang, the particle horizon, sets an absolute upper bound on structure size. Within this horizon, the finite speed of gravity's influence, combined with the finite age of the universe, ensures that only regions smaller than a few hundred megaparsecs have had sufficient time to develop significant density contrasts through gravitational interaction. The mathematical framework describing this transition employs concepts from statistical mechanics and random field theory. The universe's matter distribution can be treated as a random field, a mathematical object that assigns a density value to every point in space according to probabilistic rules. The statistical properties of this field, characterized by its power spectrum and correlation functions, determine how structure appears at different scales. A Gaussian random field, which describes the primordial fluctuations generated by inflation, possesses the special property that all its statistical information is contained in the two-point correlation function. Higher-order correlations, describing the probability of finding 3 or 4 galaxies in specific configurations, can be calculated from the two-point function alone. As gravitational evolution proceeds, however, the density field develops non-Gaussian features. Regions that collapse into clusters become highly overdense, while voids expand and empty out, creating an asymmetric distribution of densities. The cosmic web's filamentary structure reflects these non-linear effects, which become increasingly important at smaller scales. Yet on scales above the homogeneity threshold, these non-linear features average out, and the universe's statistical properties approach those of the primordial Gaussian field, modified only by the overall growth factor that describes how much fluctuations have been amplified. Observational tests of homogeneity continue to refine our understanding of this transition. Counts of galaxies in spherical shells at increasing distances should follow specific statistical distributions if the universe is truly homogeneous. Measurements of the cosmic expansion rate in different directions should yield identical results if isotropy holds. The distribution of galaxy clusters, quasars, and gamma-ray bursts across the sky should show no preferred directions or anomalous concentrations at the largest scales. Current data largely confirm these predictions, though intriguing anomalies persist. The high MB exhibits a slight asymmetry between hemispheres, with one half of the sky showing marginally stronger fluctuations than the other. Certain directions in space appear to align with the motion of the local group through the CMB rest frame in ways that might be coincidental or might hint at subtle violations of isotropy. These anomalies remain at the edge of statistical significance, tantalizing but not yet compelling. The homogeneity scale thus represents a threshold of understanding, the boundary between the structured universe of galaxies and clusters, where individual objects can be named and mapped, and the smooth universe of cosmological theory, where only statistical averages matter. Cross this threshold, and the cosmic web dissolves into uniformity, its intricate patterns fading like ripples on a pond viewed from sufficient height. But that uniformity, that remarkable sameness across hundreds of megaparsecs, itself demands explanation. For if the universe began in chaos, in the unimaginable violence of the Big Bang, how did regions separated by billions of light-years come to share the same temperature, the same density, the same fundamental properties? The answer lies in a fraction of a second so brief that it defies comprehension, a period when the universe expanded faster than light itself, stretching quantum fluctuations into the seeds that would eventually become every galaxy, every cluster, every filament in the cosmic web. This epoch is called cosmic inflation, and it lasted perhaps 10 to the minus 36 to 10 to the minus 32 seconds after the universe began. In that inconceivably brief interval, a duration so short that comparing it to a single second is like comparing a second to 10 to the 26th power years, space itself expanded by a factor of at least 10 to the 26th power, possibly far more. A region smaller than a proton ballooned to a size larger than the entire observable universe today. The expansion was not matter moving through space, but space itself stretching, carrying everything within it along for the ride at velocities that, measured against distant points, exceeded the speed of light without violating relativity's prohibition on objects moving through space faster than light. The mechanism driving this expansion remains one of physics' great mysteries, though the leading hypothesis invokes a quantum field called the inflaton. Unlike familiar fields such as electromagnetism, the inflaton field existed in a state of false vacuum, a configuration that appeared stable but contained enormous potential energy, like a ball balanced precariously on a hilltop. This energy density, estimated at roughly 10 to the 73rd power grams per cubic centimeter, a number so large it loses all intuitive meaning, generated a repulsive gravitational effect that drove space to expand exponentially. Every 10 to the negative 37th seconds or so, the universe doubled in size, and this doubling continued for perhaps 100 doublings or more. The consequences of this expansion solve several profound puzzles that plagued earlier cosmological models. Consider the horizon problem. Regions of the cosmic microwave background separated by more than about 2 degrees on the sky should never have been in causal contact. Light, even traveling since the Big Bang, has not had time to cross between them. Yet they share the same temperature to 1 part in 100,000. Without inflation, this uniformity would require an impossible conspiracy of initial conditions. With inflation, the explanation becomes elegant. These regions were once in intimate contact, sharing information and equilibrating their properties, before inflation stretched them apart faster than light could reconnect them. The flatness problem finds similar resolution. The geometry of the universe depends on its total energy density compared to a critical value. If the density exceeds the critical value by even a tiny amount, the universe curves back on itself and eventually recollapses. If it falls short, space curves the opposite way and expands forever in a geometry where parallel lines eventually diverge. Observations show the universe is flat to within 0.4%. Parallel lines remain parallel across billions of light years. But this flatness is unstable. Any deviation from perfect flatness in the early universe would have grown enormously over 13.8 billion years. For the universe to be this flat today, it must have been flat to 1 part in 10 to the 60 power at the Planck time, 10 to the minus 43 seconds after the Big Bang. Inflation explains this fine-tuning naturally. The exponential expansion stretched any initial curvature to imperceptibility, like inflating a balloon until its surface appears flat to an ant walking upon it. But inflation's most profound legacy lies not in what it smoothed away, but in what it preserved. For even as the inflaton field drove space to expand, quantum mechanics ensured that perfect uniformity remained impossible. The uncertainty principle, that fundamental law stating that certain pairs of properties cannot both be precisely defined, applied to the inflaton field itself. Tiny quantum fluctuations, random variations in the field's energy density, arose spontaneously throughout the inflating region. These fluctuations were minuscule, representing energy variations of perhaps 1 part in 100,000, but inflation stretched them from subatomic scales to cosmic ones. A fluctuation that began smaller than a proton When inflation ended, spanned distances larger than galaxy clusters span today. The quantum became classical. Random variations that existed for mere instants became frozen into the fabric of space. Their wavelengths stretched so large that they could no longer oscillate back to uniformity. These density perturbations, regions slightly denser or slightly less dense than average, became the seeds of all cosmic structure. The mathematics of this process makes specific predictions. Inflation should produce fluctuations with a nearly scale-invariant spectrum, meaning that the amplitude of density variations should be almost the same across all length scales. A region destined to become a supercluster should have started with roughly the same fractional overdensity as a region destined to become a single galaxy. The spectrum should not be perfectly scale invariant, however. Inflation predicts a slight tilt, with larger scales having marginally smaller amplitudes. This tilt, characterized by a spectral index of approximately 0.96 rather than exactly 1.00, reflects the gradual evolution of the inflaton field as inflation proceeded. The Planck satellite measured this spectral index with exquisite precision, 0.9649 plus or minus 0.0042. The deviation from perfect scale invariance, predicted by the simplest inflationary models, appears exactly where theory suggested it should. This agreement between prediction and observation, spanning a range of scales from millions to billions of light years, represents one of cosmology's greatest triumphs. Inflation also predicts that the fluctuations should be Gaussian. Their statistical distribution should follow the familiar bell curve, with most regions close to average density and progressively fewer regions at extreme over or under densities. The cosmic microwave background confirms this prediction to remarkable precision. The temperature variations across the sky, when analyzed statistically, show no significant deviation from Gaussianity. The seeds of structure were planted randomly, without preference for particular patterns or arrangements, and the structures that grew from them inherited this statistical democracy. The end of inflation came when the inflaton field finally rolled down from its false vacuum state to its true minimum, releasing its stored energy in a process called reheating. This energy converted into a hot, dense plasma of particles, quarks, electrons, photons, and all the other constituents of the early universe. The temperature after reheating may have reached 10 to the 27th Kelvin or higher, hot enough to create particles far more massive than any accelerator on Earth can produce. From this primordial soup, the universe we observe today eventually emerged. The density fluctuations imprinted during inflation survived this transition. Regions that were slightly overdense attracted slightly more matter through gravity. Regions that were slightly underdense lost matter to their denser neighbors. Over millions and then billions of years, these tiny initial differences amplified. The 1 part in 100,000 variations visible in the cosmic microwave background grew into the 1 part in 1 variations that define galaxy clusters today. Regions where matter is thousands of times denser than the cosmic average, surrounded by voids where matter is 10 times less dense. The largest fluctuations, those stretched to scales of hundreds of megaparsecs, evolved most slowly. Gravity had less time to amplify them, and dark energy began counteracting gravitational collapse before they could grow significantly. These fluctuations remain subtle even today, visible only in the statistical clustering of galaxies across enormous volumes. The baryon acoustic oscillations, those frozen sound waves spanning 500 million light-years, represent fluctuations from this primordial era, their characteristic scale set by physics in the first 380,000 years, but their existence traceable to quantum fluctuations during inflation. Smaller fluctuations, those stretched to scales of megaparsecs or tens of megaparsecs, had more time to grow. They collapsed first, forming the dark matter halos that would host the first galaxies. These early structures then merged hierarchically, building larger and larger systems until the galaxy clusters and superclusters of today emerged. Every step in this hierarchy traces back to inflation's quantum seeds, the random variations that determined which regions would become dense and which would become empty. Some inflationary models predict additional signatures that astronomers continue to seek. Gravitational waves, ripples in space-time itself, should have been generated during inflation alongside the density fluctuations. These primordial gravitational waves would leave a distinctive imprint on the polarization of the cosmic microwave background, a swirling pattern called B-mode polarization. Detecting this signal would provide direct evidence for inflation and constrain the energy scale at which it occurred. Current searches have found B-modes from gravitational lensing by intervening matter, but have not yet definitively detected the primordial signal, placing upper limits on the amplitude of inflationary gravitational waves. The quantum origins of cosmic structure remain among the most profound connections between the very small and the very large. The same uncertainty principle that governs the behavior of electrons in atoms also determined where galaxies would form billions of years later. The same quantum field theory that describes particle physics also describes the mechanism that made the universe habitable. In the seeds planted during inflation, quantum mechanics and general relativity meet, their combined predictions written across the sky in the distribution of matter and light. Those predictions, written as the quantum fluctuations of an inflating universe, would remain hidden for nearly 400,000 years. During that immense span, the cosmos existed as a seething plasma, a fog of free electrons and protons so dense that light could not travel more than a short distance before scattering. Photons ricocheted endlessly through this primordial soup, their paths randomized by constant collisions with charged particles. The universe, though filled with radiation, was utterly opaque. The temperature during this epoch defies everyday comprehension. In the first moments after inflation ended, the cosmos blazed at trillions of degrees, hot enough to create and destroy particles in endless cycles. As space expanded, this temperature dropped steadily. The same physics that makes compressed gas hot and expanding gas cool applied to the entire universe. By 1 second after the Big Bang, the temperature had fallen to roughly 10 billion Kelvin. By 3 minutes, it reached 1 billion Kelvin, cool enough for protons and neutrons to fuse into helium nuclei. But even then, the universe remained a plasma, electrons still too energetic to bind with atomic nuclei. This plasma era lasted far longer than the brief nuclear fusion epoch. For approximately 380,000 years, the universe remained ionized, its temperature gradually declining as expansion stretched space and diluted the energy of every photon. The cosmos cooled through millions of degrees, then hundreds of thousands, approaching the critical threshold where electrons would finally slow enough to be captured by nuclei. That threshold arrived when the universe reached approximately 3,000 Kelvin, roughly half the temperature of the Sun's surface. At this temperature, the typical photon no longer carried enough energy to ionize a hydrogen atom. Electrons began combining with protons, forming neutral hydrogen for the first time. This process, called recombination despite the fact that electrons and protons had never been combined before, transformed the universe from opaque plasma to transparent gas over a span of roughly 100,000 years. The transition was not instantaneous, but gradual, like fog slowly lifting from a valley. As more electrons joined with nuclei, fewer free charges remained to scatter photons. The mean free path of light, the average distance a photon could travel before hitting an electron, grew longer and longer. Eventually, that distance exceeded the size of the observable universe. Light, trapped for hundreds of thousands of years, was suddenly free to travel unimpeded across space. The photons released during recombination have been traveling ever since. They carry information about the conditions at the moment of their last scattering, a thermal snapshot of the universe when it was roughly 1,000th of its current size. These photons, stretched by 13.8 billion years of cosmic expansion, now reach Earth as microwave radiation with a temperature of 2.725 Kelvin, just 2.725 degrees above absolute zero. This cosmic microwave background, or CMB, was first detected in 1965 by Arno Penzias and Robert Wilson, radio astronomers at Bell Labs, who initially mistook the signal for antenna noise. They had stumbled upon the oldest light in the universe, radiation that had been traveling since the cosmos was less than 500,000 years old. The discovery confirmed a key prediction of Big Bang cosmology and earned them the Nobel Prize. The CMB is remarkably uniform. In every direction astronomers look, they measure nearly identical temperatures, varying by only about 1 part in 100,000. This uniformity reflects the homogeneity established during inflation, when quantum fluctuations were stretched to cosmic scales but remained tiny in amplitude. The universe at recombination was almost perfectly smooth, its density varying by mere fractions of a percent from place to place. Yet those tiny variations contain everything. The slightly denser regions, where matter had begun to clump under gravity's influence, were also slightly hotter. Compressed gas radiates more intensely. The slightly underdense regions were fractionally cooler. These temperature differences, mapped with exquisite precision by satellites like COBE, WMAP, and Planck, revealed the seeds of all cosmic structure. The Planck satellite, launched in 2009, measured CMB temperatures with an accuracy of a few millionths of a degree. Its full sky maps show a mottled pattern of hot and cold spots, each corresponding to density variations in the primordial plasma. The largest spots span several degrees on the sky, corresponding to regions roughly 500,000 light-years across at the time of recombination. The smallest detectable spots are a fraction of a degree, representing structures tens of thousands of light years in size. The statistical properties of these temperature fluctuations encode fundamental cosmological parameters. By analyzing how the amplitude of fluctuations varies with angular scale, a measurement called the power spectrum, cosmologists have determined that the universe is geometrically flat to within 0.5%. They have measured the density of ordinary matter at 4.9% of the total energy content, dark matter at 26.8%, and dark energy at 68.3%. They have established the age of the universe at 13.8 billion years and the current expansion rate at approximately 67.4 kilometers per second per megaparsec. The power spectrum reveals a series of peaks and troughs, acoustic oscillations frozen into the CMB at the moment of recombination. These peaks correspond to sound waves that had completed specific fractions of an oscillation cycle before recombination occurred. The first peak, at an angular scale of about 1 degree, represents regions that had compressed exactly once. The second peak shows regions that had compressed and then rarefied. The third peak captures a second compression. The precise positions and heights of these peaks depend sensitively on cosmological parameters, making the CMB an extraordinarily precise tool for measuring the universe's composition and geometry. The temperature fluctuations also exhibit subtle polarization patterns. As photons scattered off electrons for the last time, the geometry of each scattering event imprinted a preferred orientation on the light's electric field. This polarization comes in two types, called E modes and B modes, distinguished by their mathematical symmetry. E modes arise from density fluctuations and have been measured in detail. B modes can arise from gravitational lensing by intervening matter, or more excitingly, from primordial gravitational waves generated during inflation. Beyond the primary CMB signal, secondary effects reveal structure that formed after recombination. As CMB photons travel through the universe, they interact with matter along the way. Hot gas in galaxy clusters boosts the energy of passing photons through inverse Compton scattering, an effect called the Sunyaev-Zeldovich effect. This creates characteristic shadows and bright spots in CMB maps at specific frequencies, allowing astronomers to detect clusters billions of light years away. Gravitational lensing also distorts the CMB. Mass concentrations between us and the surface of last scattering bend the paths of photons, slightly magnifying and demagnifying different regions. By measuring these distortions, cosmologists can map the distribution of matter, including dark matter, along the line of sight. The lensing signal provides an independent check on structure formation models and helps constrain the total mass of neutrinos, ghostly particles that affect how structure grows. The CMB represents a boundary in time, a surface beyond which electromagnetic observations cannot penetrate. Before recombination, the universe was opaque. We cannot see further back using light. Yet the information encoded in those ancient photons tells us about even earlier epochs. The statistical properties of the fluctuations match predictions from inflation, supporting the theory that the seeds of structure were planted in the first fraction of a second. The remarkable uniformity of the temperature confirms that the observable universe was once in causal contact, a fact that inflation elegantly explains. In the faint glow of the cosmic microwave background, astronomers read the initial conditions of the universe. Every galaxy cluster, every cosmic filament, every vast void traces its ancestry to those primordial density variations. The patterns in the CMB are the blueprint from which all structure was built, a thermal echo of the moment when light first traveled freely through space. That blueprint, inscribed in the cosmic microwave background some 380,000 years after the Big Bang, set in motion the gravitational choreography that would shape the universe for billions of years. Dark matter gathered first, pooling in the slight overdensities, drawing ordinary matter into its gravitational wells. Galaxies formed, then clusters, then the vast filamentary web that spans the observable cosmos. For the first several billion years, this process of gravitational collapse proceeded as expected, with matter steadily clumping into ever larger structures. But something changed. Approximately 5 billion years ago, when the universe was roughly 8 billion years old, the expansion of space began to accelerate. This discovery, made in 1998 through observations of distant Type Ia supernova, fundamentally altered our understanding of cosmic evolution. Two independent teams, the Supernova Cosmology Project and the High Z Supernova Search Team, found that these stellar explosions appeared fainter than expected, meaning they were farther away than a decelerating universe would predict. The cosmos was not slowing down under gravity's pull, it was speeding up. The cause of this acceleration is called dark energy, a term that encompasses our ignorance as much as our knowledge. Whatever dark energy is, it constitutes approximately 68% of the total energy content of the universe. Dark matter accounts for about 27%, and ordinary matter, the atoms that make up stars, planets, and human beings, comprises merely 5%. The universe, it turns out, is dominated by something that pushes rather than pulls, that drives expansion rather than collapse. The simplest model for dark energy is the cosmological constant, a term Einstein originally introduced into his equations of general relativity in 1917 to create a static universe. He later called this his greatest blunder when Edwin Hubble discovered cosmic expansion. But the cosmological constant has returned, reinterpreted as the energy density of empty space itself. In this framework, every cubic meter of vacuum contains a tiny but constant amount of energy, roughly 6 times 10 to the negative 10 joules per cubic meter. This value seems absurdly small, yet when summed across the immense volume of the observable universe, it dominates all other energy contributions. The effect of dark energy on large-scale structure is profound and irreversible. During the matter-dominated era, when dark matter and ordinary matter controlled cosmic dynamics, gravity could overcome the expansion of space on scales up to hundreds of megaparsecs. Structures grew hierarchically, with small clumps merging into larger ones. But as the universe expanded, the density of matter decreased, diluted across ever greater volumes. Dark energy, by contrast, maintains a constant density as space expands. Eventually, dark energy's influence surpassed that of matter, and the balance tipped. Today, gravitational collapse can still occur within bound structures. Galaxy clusters like Coma, with its mass of approximately 7 times 10 to the 14th solar masses, remain gravitationally coherent. The Virgo cluster, some 54 million light-years away, continues to hold its 1,000-plus galaxies in gravitational embrace. Even superclusters like Laniakea, spanning 520 million light-years, maintain internal gravitational flows. But these structures are now islands in an accelerating sea. The space between superclusters stretches faster than gravity can bridge. The Hubble constant, which measures the current expansion rate, stands at approximately 70 kilometers per second per megaparsec. This means that for every megaparsec of distance, about 3.26 million light-years, galaxies recede from us at an additional 70 kilometers per second. At distances beyond roughly 14 billion light-years, this recession velocity exceeds the speed of light. Not because galaxies move through space faster than light, but because space itself expands faster than light can traverse it. These regions are forever beyond our reach, receding into permanent causal isolation. For the cosmic web, dark energy acts as a kind of structural freeze. The filaments that connect galaxy clusters will stretch and thin as expansion accelerates. Voids already comprising 80% of the universe's volume will grow emptier still. The density contrast between filaments and voids will diminish as matter becomes ever more diluted. Simulations of future cosmic evolution, run forward billions of years, show the web gradually fading, its threads attenuating like mist in morning sun. The fate of individual structures depends on their binding energy. The Milky Way and Andromeda, separated by 2.5 million light-years, are gravitationally bound and will merge in approximately 4.5 billion years, forming a larger elliptical galaxy sometimes called Milky Way. The local group, with its 80-plus member galaxies spread across 10 million light-years, will likely coalesce into a single massive galaxy over tens of billions of years. But the Virgo cluster, though gravitationally influential, lies just beyond the local group's binding reach. Dark energy will carry it away, along with the rest of the Laniakea supercluster's distant members. In the far future, trillions of years hence, observers within our merged local group galaxy would see a very different cosmos. The cosmic microwave background, stretched by expansion to wavelengths longer than the observable universe, would be undetectable. Distant galaxies, carried beyond the cosmic horizon by accelerating expansion, would redshift into invisibility and then vanish entirely from the observable universe. The night sky would contain only the stars of the local merged galaxy, surrounded by absolute darkness. The evidence for the Big Bang, for cosmic expansion, for the existence of other galaxies, all would be erased by dark energy's relentless push. This future isolation represents a kind of cosmic amnesia. The very observations that revealed dark energy's existence, distant supernovae, the cosmic microwave background, the large-scale distribution of galaxies, would become impossible. Future astronomers, if any existed, would have no way to deduce that the universe was once filled with hundreds of billions of galaxies. That space was once dense with matter, that the cosmos began in a hot, compressed state 13.8 billion years before. The evidence would have expanded beyond all possible detection. Yet this fate remains billions of years distant. Today, the cosmic web still glows with the light of countless galaxies. The filaments still channel matter toward clusters. The voids still expand, but slowly, at rates measured in megaparsecs per billion years. The universe remains young enough that its structure is visible, its history readable in the distribution of matter across space. Dark energy's nature remains one of the deepest mysteries in physics. The cosmological constant model fits observations well, but it raises profound theoretical puzzles. Quantum field theory predicts that empty space should contain vastly more energy than observed, a discrepancy of some 120 orders of magnitude, perhaps the worst prediction in the history of physics. Alternative models propose that dark energy is not constant, but dynamic, perhaps a field called quintessence that evolves over cosmic time. Some theories suggest that dark energy's strength might change, potentially even reversing in the distant future to cause a big crunch rather than eternal expansion. Current observations, including measurements of baryon acoustic oscillations and the growth rate of cosmic structure, constrain dark energy's properties with increasing precision. The Dark Energy Survey, using a 570-megapixel camera on a 4-meter telescope in Chile, has mapped hundreds of millions of galaxies to trace how structure has grown over the past 8 billion years. The results are consistent with a cosmological constant, but small deviations remain possible. Future missions, the Euclid Space Telescope, the Vera Rubin Observatory, the Nancy Grace Roman Space Telescope, will push these measurements further, seeking any hint that dark energy evolves. For now, the universe expands at an accelerating rate, carrying its structures apart on the fabric of space itself. The cosmic web, that magnificent architecture of filaments and voids, clusters and walls, represents a snapshot of a dynamic process, a universe caught between the gravitational legacy of its dense beginnings and the dark energy that will ultimately isolate its parts. Every observation of distant galaxies, every map of large-scale structure, captures this moment in cosmic history, when the universe is still young enough to be known. And yet, for all the billions of galaxies mapped, for all the filaments traced and voids measured, for all the light gathered by telescopes spanning centuries of human ingenuity, there exists a boundary beyond which no observation can ever reach. Not a wall in space, not a barrier of matter, but something more fundamental, a horizon defined by the finite speed of light and the finite age of the universe itself. This is the edge of the observable universe, and understanding its nature reveals both the power and the profound limitations of cosmic cartography. The observable universe extends approximately 46.5 billion light-years in every direction from Earth. This number seems paradoxical at first. How can we see objects 46 billion light-years away in a universe only 13.8 billion years old? The answer lies in cosmic expansion. Light that left a distant galaxy when the universe was young has been traveling toward us while space itself stretched beneath it, like a message passed along an expanding conveyor belt. The galaxy that emitted that light has been carried even farther away during the journey. When astronomers detect the most distant galaxies, they see objects as they appeared over 13 billion years ago. But those same objects now reside roughly 46 billion light-years distant, receding at speeds that exceed light itself. Not through space, but with space as it expands. This creates a sphere centered on every observer, a personal cosmic horizon containing everything that could ever have sent light in time to reach that location. The volume of this sphere encompasses approximately 4 times 10 to the 80 cubic meters, containing an estimated 2 trillion galaxies, each with hundreds of billions of stars. The total number of stars within the observable universe approaches 10 to the 24th power, a number so vast that writing it requires 24 zeros, more stars than grains of sand on every beach on Earth, multiplied 1,000-fold. The edge of this observable sphere is not a place one could visit. It represents a moment in time more than a location in space. The surface of last scattering, whereas cosmic microwave background originated 380,000 years after the Big Bang. Beyond this surface, the universe was opaque, filled with the plasma that scattered photons before atoms could form. No electromagnetic signal from earlier epochs can reach us directly. That era remains hidden behind a wall of its own light. But the observable universe is not the whole universe. Cosmological models, constrained by the remarkable flatness of space, measured to within 0.4%, suggest that the total universe extends far beyond what we can see. If the universe is truly flat, if parallel lines remain parallel forever, then it may be infinite, stretching endlessly in all directions with the same statistical properties observed locally. Alternatively, if space curves ever so slightly, the universe might be finite but unbounded, like the surface of a sphere where traveling far enough in one direction returns you to your starting point. Current measurements cannot distinguish between these possibilities, but they do constrain the minimum size. If the universe curves back on itself, its total circumference must exceed 78 billion light-years, making the observable portion a small fraction of the whole. The concept of the particle horizon formalizes this boundary. It represents the maximum distance from which particles, including photons, could have traveled to reach an observer since the beginning of time. This horizon has been expanding since the Big Bang, not because space is being added at the edge, but because light from ever more distant regions has finally had time to arrive. Every second, the particle horizon grows by roughly 300,000 kilometers, the distance light travels in that time. Yet this growth is now losing the race against cosmic expansion. Galaxies beyond a certain distance, the Hubble radius, currently about 14.4 billion light-years, are receding faster than light due to the expansion of space between us. Light emitted from those galaxies today will never reach Earth, no matter how long the universe endures. This creates a second, more troubling boundary: the event horizon of the observable universe. Unlike the particle horizon, which describes what we can see from the past, the event horizon describes what we will ever be able to see in the future. Due to the accelerating expansion driven by dark energy, this horizon is shrinking in co-moving coordinates. Galaxies currently visible will eventually cross this threshold, their light red-shifted beyond detection, their futures forever hidden from our descendants. The local group, Our gravitational family, including the Milky Way and Andromeda, will remain bound together, but the larger cosmic web will fade from view over hundreds of billions of years. The uniformity of the observable universe across its vast expanse presents one of cosmology's deepest puzzles, resolved by inflation. Regions on opposite sides of the cosmic microwave background sky, separated by 93 billion light-years today, display temperatures matching to 1 part in 100,000. Yet in a universe without inflation, these regions could never have been in causal contact. Light would not have had time to travel between them, even at the beginning. Inflation solves this by proposing that all observable regions once occupied a volume smaller than an atom, achieving thermal equilibrium before being stretched to cosmic scales in a fraction of a second. The observable universe, in this view, is a tiny patch of a much larger post-inflationary domain, homogenized by processes that occurred before the conventional Big Bang expansion began. The large-scale structure within this observable volume, the cosmic web of filaments and voids, the superclusters and walls mapped by redshift surveys, represents the gravitational evolution of quantum fluctuations stretched to astronomical scales. These structures are not random. They encode information about the physics of the early universe, the nature of dark matter, the properties of dark energy. Every galaxy cluster, every void, every filament serves as a data point in humanity's attempt to understand the cosmos. The Sloan Great Wall, the Hercules Corona Borealis Great Wall, the Laniakea Supercluster. These are chapters in a story written by gravity over 13.8 billion years, readable only because light has carried their images across the expanding gulf of space. The temperature of the observable universe, averaged across all of space, is 2.725 Kelvin, the remnant glow of the cosmic microwave background that fills every cubic centimeter with approximately 411 photons. This radiation dominates the energy density of the cosmos in terms of particle number, though dark energy now dominates in terms of gravitational effect. The universe is cold, dark, and nearly empty, with an average density of roughly 6 protons per cubic meter when all matter, visible and dark, is smoothed across its volume. Most of space is void, and most of the matter is invisible, detectable only through its gravitational influence on the structures we can see. At the largest scales, the observable universe approaches homogeneity. Beyond 300 megaparsecs, the statistical properties of matter distribution become uniform in all directions. This cosmological principle, that no location is special, that the universe looks the same everywhere on sufficiently large scales, underpins all of modern cosmology. It allows scientists to extrapolate from local observations to universal laws, to assume that the physics governing distant galaxies matches the physics measured in laboratories on Earth. Without this assumption, cosmology would be impossible. With it, the entire observable universe becomes a laboratory for testing fundamental physics. The boundary of observation is also a boundary of knowledge. Beyond the cosmic microwave background lies an era accessible only through gravitational waves and neutrinos, messengers that decoupled from matter even earlier than photons. Future detectors may probe the gravitational wave background from inflation itself, opening a window onto the first trillionth of a second. But electromagnetic astronomy, the foundation of everything known about the cosmos, reaches its fundamental limit at the surface of last scattering, 380,000 years after the beginning. And so the observable universe stands as both triumph and limitation. It contains more galaxies than any human could count in a lifetime, more stars than words ever spoken, more structure than centuries of study could fully map. Yet it represents only what light has had time to reveal, a sphere of knowledge in an ocean of unknown extent. The cosmic web stretches to its edges and presumably beyond, filaments and voids continuing in patterns we can only infer. The universe may be infinite or merely unimaginably large, its true nature hidden behind horizons that recede faster than light can chase. What remains is wonder, grounded in measurement, the recognition that even the edge of knowledge is itself a discovery, a boundary mapped by the patient accumulation of photons across billions of years.